We look up at the stars, but there are places where stars are swallowed, where light cannot escape and time stands still. Tonight we will travel to such a place, not just to the edge, but through it. Could we survive a journey to the center of a black hole? Let us begin. In the vast emptiness of space, in the darkness between stars, there exist objects so dense, so powerful, that they bend the very fabric of reality. These cosmic entities pull everything toward them, even the light that allows us to see. They are invisible against the backdrop of space, detectable only by their effects on surrounding matter and energy. Black holes represent the ultimate mystery of our universe. They are where our understanding of physics begins to unravel, where time and space behave in ways that defy our everyday experience. They are cosmic enigmas that challenge our most brilliant minds and inspire our wildest imaginations. Tonight, we embark on an impossible journey, a journey no human could physically survive, yet one we can explore through the power of science and imagination. We will venture toward the most extreme environment known to exist, a place where gravity becomes infinite and the laws of physics as we know them cease to function. What happens when we approach a black hole? What would we see as we cross the threshold known as the event horizon? Could anything or any information ever escape from within? These questions have fascinated astronomers, physicists, and dreamers for generations. Our journey will take us through curved space-time, past swirling disks of superheated matter, and into regions where reality itself seems to fold and compress. We will contemplate not just the physical reality of these cosmic monsters, but also the philosophical implications of their existence. Are black holes the end of information? Or could they be gateways to other universes, other possibilities? What would it mean for human consciousness to encounter such a place? As we drift towards sleep, let us drift toward the ultimate cosmic abyss and wonder at what lies beyond. In this gentle exploration, we will move step by step from the familiar to the unknowable. We will respect what science tells us while embracing the wonder of what remains uncertain. Our journey begins not with fear of the darkness, but with curiosity about what secrets it might hold. Picture yourself floating in the void of space. Around you, stars twinkle against the blackness, distant suns burning brightly in the cosmic night. But ahead of you lies something different, a region where the stars seem to disappear, where the darkness is deeper, more profound. This is not just an absence of light, but a place where light itself is drawn in, never to return. As you drift closer, you notice something strange. The stars behind this dark region appear to bend, to curve around it, as if the very fabric of space were being pulled like a sheet. This is your first glimpse of a black hole's power, its ability to warp the space-time around it so severely that even light must follow curved paths in its presence. The silence of space surrounds you. Here, in the vacuum between worlds, there is no sound. Yet if we could translate the gravitational forces into audio, what would we hear? Perhaps a deep, resonant hum, a cosmic bass note playing at the edge of perception, the song of extreme gravity, calling everything toward its center. As you move closer still, time itself begins to change. You would not notice it yourself, but to an observer watching from a great distance, you would appear to slow down. Your movements, the beating of your heart, even the firing of neurons in your brain, all would seem to stretch out, to happen more and more gradually the closer you approach to the black hole's embrace. This is the nature of gravity's effect on time. Near these cosmic titans, time flows differently. What might seem like moments to you could be years, centuries, or even millennia to someone watching from Earth. You're not just traveling through space, but through time as well, stretching and bending the very rhythm of existence as you venture closer to the abyss. Around some black holes, matter accumulates in what astronomers call an accretion disk. Gas, dust, and even torn-apart stars spiral inward, heating to millions of degrees as they compress and collide. These disks shine brightly across the electromagnetic spectrum, from radio waves to X-rays, creating some of the most luminous objects in the universe. A beautiful, deadly dance of matter in its final moments before disappearing forever. Yet despite this brightness at the edges, the black hole itself remains invisible, a shadow against the cosmos, a void that swallows rather than reflects. We cannot see it directly, only its effects on the universe around it. It is defined by absence, by what is no longer there, by what has been removed from our view. In our journey tonight, we will approach this absence. We will contemplate its nature and its mysteries. We will ask what it means for something to exist that cannot be seen, only inferred. We will wonder at the paradoxes and possibilities that arise when gravity becomes so strong that the rules of reality seem to break down. So close your eyes and imagine looking up at a night sky filled with stars. And there, in the distance, is a place where stars go to disappear. That is our destination tonight, a place of impossible gravity where even light cannot escape. A black hole awaits us, not with malice or hunger, but with the silent, patient power of natural law taken to its extreme. Our journey begins now, into the darkness, into the unknown, into the heart of cosmic mystery. Before we fall in, we must first understand what we are falling into. A black hole is not truly a hole. It is not empty space, nor is it a tunnel leading somewhere else, at least not as far as we know with certainty. Rather, it is an extraordinary concentration of matter, compressed into a volume so small that the force of gravity overcomes all other forces in nature. Imagine taking the Earth and squeezing it, compressing all its mountains and oceans, its core and crust, down to the size of a marble. The gravity of that marble would still be equal to the gravity of Earth, but concentrated in a far smaller area. Now imagine continuing to compress, making that marble smaller and smaller until it becomes the size of a grain of sand, then an atom, then smaller still. At some point in this compression, gravity becomes so intense that not even light, the fastest thing in our universe traveling at approximately 300,000 kilometers per second, can escape its pull. This is the essential nature of a black hole. It is matter compressed beyond a critical threshold, creating gravity so powerful that it traps everything, even light itself. The term black hole was coined relatively recently, in 1967, by American physicist John Wheeler. But the concept had been predicted much earlier as a consequence of Albert Einstein's general theory of relativity. In 1916, just months after Einstein published his groundbreaking work, German physicist Karl Schwarzschild found a solution to Einstein's equations that described what we now call a black hole. The defining feature of a black hole is its event horizon. This is not a physical surface, but a boundary in space. It marks the region beyond which nothing can return to the outside universe. Anything, whether matter or light, that crosses this boundary is forever trapped within the black hole's gravitational influence. The size of this event horizon, known as the Schwarzschild radius, depends on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would be just about 6 kilometers in radius. For one with the mass of Earth, it would be less than a centimeter. And for the supermassive black holes that lurk at the centers of galaxies, including our own Milky Way, the event horizon can be millions or even billions of kilometers across. At the theoretical center of a black hole lies what physicists call a singularity. Here, according to our current understanding, matter is compressed to infinite density and space-time curves infinitely. This is where our physics breaks down, where the equations that describe the universe stop making sense. The singularity represents both the limit of our knowledge and a frontier for new theoretical work. But how do black holes form? The most common type begins as a star, not unlike our Sun, though considerably more massive. Stars are cosmic balancing acts, with the inward pull of gravity counteracted by the outward pressure of nuclear fusion in their cores. When a massive star exhausts its nuclear fuel, this balance is disrupted. Without the outward pressure from fusion, gravity takes over. The star's core collapses inward upon itself with catastrophic force. If the star is massive enough, at least several times the mass of our Sun, no known force can stop this collapse. The star's outer layers may be expelled in a spectacular supernova explosion, but the core continues to collapse, potentially forming a black hole. This process creates what we call a stellar mass black hole, with a mass typically between about 5 and several tens of solar masses. But there are other types as well. Supermassive black holes found at the centers of most galaxies have masses millions or billions of times that of our Sun. How these giants formed remains an active area of research. Did they grow from stellar mass black holes that merged and consumed matter over billions of years? Or did they form directly from the collapse of enormous clouds of gas in the early universe? Perhaps both mechanisms played a role. There may also be intermediate mass black holes with masses hundreds to thousands of times that of our Sun. These could represent a missing link between stellar and supermassive varieties. And some theories suggest the existence of primordial black holes, formed not from stars, but from density fluctuations in the earliest moments after the Big Bang. But if black holes trap light, making them invisible against the black of space, how do we know they exist? We detect them indirectly, through their effects on their surroundings. When matter falls toward a black hole, it heats up due to friction and compression, often forming a swirling accretion disk that glows brightly across multiple wavelengths of light. X-ray telescopes in particular have detected numerous such systems, providing strong evidence for stellar mass black holes. For supermassive black holes, we observe their gravitational influence on nearby stars. Stars orbit the centers of galaxies at speeds that can only be explained by the presence of incredibly massive yet invisible objects. In our own Milky Way, astronomers have tracked stars orbiting an unseen object called Sagittarius A star, with a mass of about 4 million times that of our Sun, concentrated in a surprisingly small region. Perhaps the most compelling evidence came in 2019, when the Event Horizon Telescope collaboration released the first direct image of a black hole, specifically the supermassive black hole at the center of galaxy Messier 87. The image shows not the black hole itself, which remains invisible, but the glowing ring of superheated gas around it, with a dark central shadow representing the event horizon. In 2015, and again in 2017, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves, ripples in space-time, produced by pairs of black holes spiraling into each other and merging. These observations not only confirmed another prediction of Einstein's general relativity, but also provided a new window into the lives and deaths of black holes. Black holes remind us of the extreme diversity of our universe. They represent matter in perhaps its most exotic state, where density becomes effectively infinite and the familiar laws of physics approach their breaking point. They are natural laboratories for testing our most fundamental theories about space, time, and gravity. The journey to understanding black holes has been long and filled with theoretical challenges. After Schwarzschild's initial mathematical description, it took decades for physicists to fully appreciate that these objects could actually exist in nature, not just as mathematical curiosities. In the 1960s and 70s, theoretical work by physicists like Roger Penrose, Stephen Hawking, and Kip Thorne helped to establish the modern theory of black holes. Hawking in particular made the groundbreaking discovery that black holes are not entirely black. Through quantum mechanical processes occurring near the event horizon, black holes emit what is now called Hawking radiation. This radiation is incredibly faint for large black holes, but becomes significant for very small ones. Over enormously long timescales, measured in the order of 10 to the power of 67 years for stellar mass black holes, this radiation can cause black holes to lose mass and eventually evaporate completely. This discovery resolved a profound paradox about information loss in black holes. If information about matter falling into a black hole was permanently lost, this would violate a fundamental principle of quantum mechanics. Hawking radiation suggested a mechanism by which this information might be preserved, though exactly how remains an active area of research at the frontier of theoretical physics. When we observe a black hole from a distance, we do not see the event horizon itself. Rather, we see what physicists call the photon sphere, a region where light can orbit the black hole in unstable circular paths. This lies outside the event horizon at a distance of 1.5 times the Schwarzschild radius. Light from behind the black hole can be bent around this sphere, creating a distorted image of the background stars and galaxies. The mathematics that describes black holes reveals their strange properties. A non-rotating black hole, known as a Schwarzschild black hole, is perfectly spherical. Add rotation, and you get a Kerr black hole, which bulges at the equator due to centrifugal forces. If the black hole also has electric charge, it becomes a Kerr-Newman black hole, with even more complex properties. Most black holes in nature are likely rotating, as they form from the collapse of rotating stars or from the merger of objects with angular momentum. This rotation affects the space-time around them, creating a phenomenon called frame dragging, where space itself is pulled around the black hole like honey being stirred with a spoon. The power of a black hole's gravity creates extreme conditions in its vicinity. Matter falling toward a stellar mass black hole is accelerated to speeds approaching that of light. As particles of gas collide at these tremendous velocities, they generate temperatures of millions of degrees. This superheated plasma emits across the electromagnetic spectrum, from radio waves to gamma rays, creating some of the most energetic phenomena in the universe. When two black holes orbit each other, they gradually lose energy through gravitational waves, causing their orbits to decay. Eventually, they spiral together and merge in an event that, for a fraction of a second, can release more energy than all the stars in the observable universe combined. Yet this energy is not in the form of light, but of gravitational waves, ripples in the fabric of space-time itself. If our sun were to suddenly become a black hole, which it cannot due to insufficient mass, Earth's orbit would remain unchanged. Contrary to popular belief, a black hole does not have a special sucking or pulling power beyond its mass. The Earth is bound to the sun by the sun's mass, not by its size or density. However, without the sun's light and heat, Earth would quickly freeze, making life as we know it impossible. The boundary of a black hole, the event horizon, has some remarkable mathematical properties. Its surface area never decreases over time, a property reminiscent of entropy in thermodynamics. Indeed, theoretical physicists have developed a deep connection between black hole physics and thermodynamics, with the surface area of the event horizon proportional to the black hole's entropy, a measure of its disorder or information content. Black holes can grow by absorbing matter or merging with other black holes. When matter falls into a black hole, its mass, charge, and angular momentum are added to the black hole's own. Remarkably, no other properties survive. If a black hole consumes a star, the star's complex structure, its chemical composition, its magnetic fields all vanish, leaving only these three parameters. This is known as the no-hair theorem, as black holes are characterized by just these few quantities, with no additional features or hair. Some theoretical models, particularly those incorporating aspects of string theory, suggest that what we perceive as a singularity might actually be a region of extremely high, but not infinite, density. In these models, the seemingly fundamental particles of our standard model of physics are actually tiny, vibrating strings, and the laws of physics at these scales might prevent the formation of a true mathematical singularity. Another possibility is that at the heart of a black hole, space-time transitions into something else entirely. Perhaps a region where space and time, as we understand them, cease to be meaningful concepts. This could connect to theories of quantum gravity, attempts to reconcile Einstein's general relativity with quantum mechanics, which remain one of the greatest challenges in theoretical physics. As we contemplate black holes, we stand at the edge of our scientific understanding. These objects represent extremes of nature, pushing our theories to their limits and beyond. They are cosmic laboratories for testing ideas about quantum gravity, the nature of space-time, and the ultimate fate of matter. In the silent depths of space, black holes wait, not as monsters or devourers, but as profound expressions of the universe's underlying laws. They are endings, yes, for the matter that falls into them, but they are also beginnings, starting points for new understanding, new theories, new ways of seeing the cosmos. And so we prepare to journey deeper, to explore the warped space-time around a black hole, to understand how these objects bend not just light, but the very fabric of reality. We prepare to approach the event horizon, that boundary beyond which no return is possible. But first, we must understand more about the nature of space-time itself, the canvas upon which the black hole paints its presence. Gravity is not just a force, it is the shape of reality. And near a black hole, that shape begins to twist. To understand black holes, we must first understand gravity. And to understand gravity as it truly operates in our universe, we must embrace one of the most revolutionary scientific ideas ever conceived: Einstein's general theory of relativity. Before Einstein, scientists viewed space and time as separate, unchanging backdrops against which the events of the universe played out. Space was thought of as an empty stage, an absolute grid extending infinitely in all directions. Time was seen as flowing uniformly everywhere, ticking forward at the same rate for all observers. Isaac Newton's laws of motion and gravity had served humanity well for centuries. They predicted the movements of planets with remarkable accuracy. They helped engineers build bridges and buildings. They explained the arcs of cannonballs and the orbits of moons. But there were hints, subtle discrepancies, suggesting that something deeper was at work. In 1905, Albert Einstein published his special theory of relativity, showing that space and time were not separate entities, but aspects of a unified whole, space-time. He demonstrated that time could flow at different rates for observers moving at different speeds. The faster you move through space, the slower you move through time. But this was just the beginning. 10 years later, in 1915, Einstein completed his general theory of relativity. This theory transformed our understanding of gravity itself. Gravity, Einstein proposed, is not a force being exerted across space, as Newton had described it. Rather, it is the result of the curvature of space-time caused by the presence of mass and energy. Imagine space-time as a vast rubber sheet stretched taut. Place a heavy ball, representing a star, on this sheet. The ball creates a depression, a curvature in the sheet. Now roll a smaller ball past the first one. The smaller ball follows the curved surface, its path bending around the depression. This is not because the first ball is pulling on the second with some mysterious force. It is because the second ball is following the shortest path through curved space. This is how gravity works in Einstein's theory. Massive objects like stars and planets curve the space-time around them. Other objects, even light itself, follow these curves, which we perceive as the effects of gravity. As John Wheeler, the same physicist who coined the term black hole, famously summarized, matter tells space how to curve. Space tells matter how to move. Einstein's equations describing this relationship between matter and space-time curvature are notoriously complex. They consist of 10 interrelated differential equations that, in their complete form, few people on Earth can claim to fully understand. Yet their implications have been tested repeatedly over the past century, and they have passed every test with flying colors. One of the most striking predictions of general relativity was confirmed just 4 years after Einstein published his theory. During a total solar eclipse in 1919, astronomers observed that light from distant stars was deflected as it passed near the Sun, just as Einstein had predicted. The Sun's mass had curved space-time, and the starlight followed this curvature. Another prediction was that gravity could affect time directly. Clocks placed at different heights in a gravitational field would tick at different rates. A clock on the ground floor of a building runs slightly slower than one on the top floor because it sits deeper in Earth's gravitational well, where space-time is more curved. This effect, known as gravitational time dilation, has been measured with atomic clocks of extreme precision, confirming Einstein's predictions to remarkable accuracy. These effects become dramatically more pronounced near a black hole, where the curvature of space-time is extreme. At the event horizon, time dilation becomes infinite from the perspective of a distant observer. If you were watching someone fall toward a black hole, you would see them appear to slow down as they approach the event horizon, eventually seeming to freeze in place. Light emitted from near the event horizon undergoes a similar effect, being stretched to longer wavelengths as it climbs out of the black hole's gravitational well. This is called gravitational redshift. Light from very close to the event horizon is shifted so dramatically that it becomes undetectable, contributing to the black appearance of the black hole. Another important concept in general relativity is the idea of geodesics, the shortest paths through curved space-time. In flat space-time, geodesics are straight lines, but in curved space-time, they can be complex curves. Objects moving solely under the influence of gravity follow geodesics, paths that appear curved to us, but are actually the straightest possible paths through the curved space-time. This leads to one of the most profound insights of general relativity, the equivalence principle. Einstein realized that being in a gravitational field is indistinguishable from being in an accelerating reference frame. If you were in a sealed elevator accelerating upward, you would feel a force pushing you down toward the floor, identical to the force you feel standing on Earth due to gravity. Similarly, if you were in a sealed elevator in free fall, you would feel weightless, just as astronauts do in orbit. This weightlessness is not because gravity has disappeared, but because both you and your surroundings are falling together, following the same geodesic through space-time. This is what we mean when we say that gravity is not a force in general relativity. It is a manifestation of the geometry of space-time. Objects are not pulled toward Earth. Rather, they are following the straightest possible paths through a curved space-time, paths that happen to lead toward Earth's center. In the extreme environment near a black hole, these concepts take on new significance. As you approach a black hole, the curvature of space-time becomes so severe that all possible future paths lead inward, toward the singularity. At the event horizon itself, the curvature reaches a critical point where even light cannot follow a path that leads away from the black hole. Yet from the perspective of someone falling into a black hole, nothing special would seem to happen at the event horizon itself. There is no physical barrier, no wall or membrane. You would not feel yourself crossing a boundary. This is because locally, space-time remains relatively smooth. It is only when viewed from a distance that the extreme curvature becomes apparent. The concept of space-time curvature can be difficult to visualize because we naturally think of space as three-dimensional and time as one-dimensional, making space-time four-dimensional. Our minds struggle to picture curvature in 4 dimensions, but mathematically, this curvature can be precisely described, and its effects on the motion of objects and the behavior of light can be calculated with extraordinary accuracy. Near a black hole, the effects of space-time curvature manifest in several ways. One is the bending of light paths, causing straight lines of sight to curve, and creating distorted, sometimes multiple images of objects behind the black hole. This phenomenon, called gravitational lensing, has been observed throughout the universe, confirming another prediction of general relativity. Another effect is the precession of orbits. Mercury's orbit around the Sun, for example, precesses or rotates slightly more than Newtonian physics predicts. This additional precession, about 43 arc-seconds per century, was one of the first confirmations of Einstein's theory. Near a black hole, this precession would be dramatically more pronounced, causing orbits to trace complex rosette patterns rather than simple ellipses. Frame dragging is yet another effect, occurring around rotating black holes. A rotating mass drags the fabric of space-time around with it, similar to how a spinning ball in honey would drag the surrounding honey along. This means that space itself is being pulled around the black hole, affecting the motion of anything nearby. Gravitational waves, ripples in space-time that propagate at the speed of light, also emerge from Einstein's equations. These waves are produced by accelerating masses, particularly in systems like binary black holes or neutron stars. As these dense objects orbit each other, they create waves that carry away energy and angular momentum, causing their orbits to decay until they eventually merge. The detection of gravitational waves by LIGO in 2015 confirmed this aspect of general relativity and opened a new window on the universe. We can now detect events like black hole mergers that emit little or no electromagnetic radiation, allowing us to study the universe in an entirely new way. Time dilation near a black hole can be extreme. If you were hovering near the event horizon of a stellar mass black hole, each second you experienced might correspond to hours, days, or even years for observers far away. This is not just a perceptual effect, it is a real difference in the rate at which time passes, a consequence of the severe curvature of space-time. The space around a black hole is often described as being funnel-shaped, with the black hole at the bottom of the funnel. But this is only a partial visualization. The actual geometry is more complex and involves the curvature of time as well as space. Near the event horizon, the future light cones, the paths that light and therefore all causally connected events can take, tip inward, pointing toward the singularity. The Schwarzschild solution to Einstein's equations, which describes the space-time around a non-rotating uncharged black hole, predicts that at the event horizon, time and space effectively switch roles. Outside the event horizon, time marches forward, and you can move freely in space. Inside, the role of time is played by the radial coordinate. You can no more avoid moving toward the singularity than you can avoid moving forward in time. This leads to a profound realization. Inside the event horizon, the singularity is not just a place in space. It is a moment in time, a future that cannot be avoided. Just as we inevitably move from Tuesday to Wednesday, an object inside the event horizon inevitably moves toward the singularity. The black hole's intense gravity also affects the energy of light. Light climbing out of a gravitational well loses energy, shifting to longer, redder wavelengths. This gravitational redshift becomes extreme near a black hole. Light emitted just outside the event horizon would be so redshifted that it would become practically undetectable to distant observers. For rotating black holes, described by the Kerr solution to Einstein's equations, the space-time is even more complex. These black holes have two horizons, an outer event horizon and an inner Cauchy horizon. Between these lies the ergosphere, a region where space-time is dragged around so severely that nothing can remain stationary relative to distant observers. Inside the ergosphere, all objects must rotate in the same direction as the black hole, a phenomenon known as frame dragging. This rotation can be so powerful that it provides a mechanism for extracting energy from the black hole through the Penrose process, named after mathematician Roger Penrose, who first described it. Black holes also have a photon sphere, a region where light can orbit the black hole in unstable circular paths. For a non-rotating black hole, this sphere lies at 1.5 times the Schwarzschild radius. Light that passes closer than this but does not cross the event horizon will be bent back out into space, creating complex light paths that can produce multiple images of the same object. The event horizon itself has remarkable properties. It always increases in area when matter or energy falls into it, or when black holes merge, a property reminiscent of entropy in thermodynamics. Indeed, Jacob Bekenstein and Stephen Hawking showed that the event horizon's area is proportional to the black hole's entropy, with each unit of area corresponding to a fundamental unit of information. If we were to approach a black hole, we would first notice subtle gravitational effects. Stars behind the black hole would appear displaced from their true positions due to gravitational lensing. As we moved closer, this lensing would become more pronounced, with stars near the apparent edge of the black hole stretching into arcs and even forming complete rings. Closer still, we would begin to feel tidal forces, the difference in gravitational pull between the parts of our body closer to and farther from the black hole. For a supermassive black hole, these forces would initially be mild, perhaps just a gentle tugging sensation. For a stellar mass black hole, they would become lethal much sooner, tearing apart any approaching object long before it reached the event horizon, a process astronomers call spaghettification. As we approach the event horizon, if we somehow survived the tidal forces, we would notice extreme time dilation. Our communication with the outside world would become increasingly delayed from our perspective, and eventually impossible as we crossed the horizon. But from our point of view, we would not notice anything special about crossing this boundary. Space-time would continue to seem locally normal, even as it led inexorably toward the singularity. Understanding space-time and gravity through the lens of general relativity is essential for comprehending black holes. These cosmic objects are not aberrations or exotic curiosities. They are natural consequences of the way mass and energy curve space-time, the culmination of the same gravitational physics that keeps our feet on the ground and Earth in orbit around the Sun. Black holes remind us that reality is not always what it seems. Our intuitive understanding of space and time, shaped by our everyday experiences in weak gravitational fields, breaks down in these extreme environments. Yet the underlying physical laws remain consistent, even as they produce outcomes that challenge our imagination. As we continue our theoretical journey toward a black hole, we carry with us this new understanding of gravity, not as a force pulling us in, but as the shape of reality guiding our path. We recognize that the seemingly empty space around us is actually a rich, dynamic geometry, responding to the presence of matter and energy. And we prepare ourselves for the next step, approaching the ultimate boundary in physics, the event horizon itself. Once you cross it, you are no longer part of the universe we know, the event horizon. Perhaps no concept in physics is simultaneously so simple and so profound. It is a boundary in space, a threshold beyond which the gravitational pull of a black hole becomes so strong that nothing, not matter, not light, not information of any kind, can escape back to the outside universe. Yet this boundary is not a physical surface. There is no wall, no membrane, no barrier that you could touch or see. If you were falling toward a black hole, you would pass through the event horizon without feeling anything unusual. There would be no jolt, no sudden change in your immediate surroundings. The laws of physics would continue to operate as they always have. This is what makes the event horizon so remarkable. It is a point of no return, a cosmic watershed defined not by what is there, but by what can no longer happen afterward. After crossing the event horizon, all possible future paths lead inevitably to the singularity at the black hole's center. The direction outward simply ceases to exist as a possibility. The term event horizon was coined in 1958 by physicist Wolfgang Rindler, though the concept had been understood earlier. Its name reflects its nature. Horizon, because like the horizon at sea, it marks the limit of what can be seen. Event, because after crossing it, no events that occur can ever be observed from the outside. For a non-rotating, uncharged black hole, the event horizon is a perfect sphere. Its radius, the Schwarzschild radius, depends only on the black hole's mass. For each solar mass, the radius increases by about 3 kilometers. So a black hole with the mass of our Sun would have an event horizon about 6 kilometers in radius. One with the mass of Earth would have an event horizon smaller than a centimeter. The supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star, has a mass of about 4 million suns and an event horizon roughly 12 million kilometers in radius, about 17 times the radius of our Sun. The black hole at the center of the galaxy, Messier 87, the first ever to be directly imaged, is about 6.5 billion times more massive than our Sun, with an event horizon larger than our entire solar system. The event horizon size scales linearly with mass, which leads to an important insight. For a stellar mass black hole, the tidal forces near the event horizon are extreme. Any object approaching would be stretched and compressed so violently that no known material could withstand the strain. But for a supermassive black hole, the tidal forces at the event horizon are much milder. In fact, for a black hole with a mass of about 100 million suns or more, you could cross the event horizon without experiencing tidal forces strong enough to be lethal. This is because while the strength of gravity at the event horizon increases with mass, the gradient of the gravitational field, which causes tidal forces, decreases with mass. Imagine the difference between falling off a cliff and rolling down a gentle hill. The change in height is more gradual on the hill, even if the total height might be greater. What would it look like to observe someone falling into a black hole? From a safe distance, you would see something remarkable. As they approach the event horizon, the light from them would be increasingly redshifted by the black hole's gravity. They would appear to move more and more slowly, their image reddening and dimming. At the event horizon itself, time dilation becomes infinite from your perspective. The infalling person would appear to freeze, their image becoming redder and fainter until it disappeared altogether. But they would never quite reach the horizon in your reference frame. To you, watching from a distance, they would seem to take an infinite amount of time to cross a boundary that, to them, takes only a finite time to traverse. This is not an optical illusion, but a fundamental property of space-time near a black hole. The severe curvature of space-time causes time to flow at dramatically different rates, depending on your position relative to the black hole. From the perspective of the person falling in, however, nothing special happens at the event horizon. They continue to experience time normally. They can look outward and see the universe, though with strange optical effects. Light from distant objects gets blue shifted as it falls in with them, while they see the universe outside evolving at an accelerated pace. One way to understand the event horizon is to consider light cones, the paths that light, and therefore all causally connected events, can take through space-time. Outside the black hole, light cones point predominantly in the time direction, allowing movement in any spatial direction. But the closer you get to the event horizon, the more these light cones tip toward the black hole. At the event horizon itself, the light cones tip so completely that one side, the side pointing outward, lies along the horizon. Light aimed directly outward from the event horizon will simply orbit the black hole forever, never escaping to infinity, but never falling in either. Inside the horizon, all light cones point toward the singularity. This means that all possible future paths, not just the path of light, but the future of anything that has crossed the horizon, lead inexorably inward. It would be as impossible to avoid moving toward the singularity as it would be to avoid moving forward in time itself. This inevitability is built into the geometry of space-time within the event horizon. It is not a question of having enough rocket power or finding the right trajectory. No physical process consistent with our understanding of nature could reverse the journey once the horizon has been crossed. The event horizon also marks a boundary for information. Any information about what happens inside the event horizon cannot reach the outside universe through normal physical processes. This leads to what physicists call the black hole information paradox, a profound challenge to our understanding of quantum mechanics, which insists that information cannot be truly destroyed. Stephen Hawking's discovery that black holes emit radiation, now called Hawking radiation, was a significant step toward addressing this paradox. This radiation, produced by quantum effects near the event horizon, causes black holes to lose mass over time and eventually evaporate completely. The question of whether and how this radiation carries information about what fell into the black hole remains an active area of research at the frontier of theoretical physics. The event horizon has another remarkable property. Its surface area never decreases under normal processes. When matter falls into a black hole, the horizon's area increases. When two black holes merge, the final black hole has an event horizon with an area at least as great as the sum of the areas of the original horizons. This property, proven by Stephen Hawking, is reminiscent of the second law of thermodynamics, which states that the entropy or disorder of an isolated system never decreases. Indeed, Hawking and others showed that the area of the event horizon is directly proportional to the black hole's entropy. Each unit of area on the horizon corresponds to a fundamental unit of information, suggesting a deep connection between gravity, quantum mechanics, and information theory. This connection has led to the holographic principle, the idea that all the information contained in a volume of space can be represented on the boundary of that region. For a black hole, this would mean that all the information about what fell in is somehow encoded on the event horizon. While initially counterintuitive, this principle has become a guiding concept in theoretical physics, particularly in approaches to quantum gravity, like string theory. The event horizon also plays a central role in thought experiments about the nature of quantum mechanics. The most famous is the black hole firewall paradox, which suggests that the event horizon cannot be the seamless boundary that general relativity describes. Instead, it might be a violent environment where the fundamental principles of physics come into conflict. This remains an unsolved problem, pointing to the need for a more complete theory that unifies general relativity and quantum mechanics. Despite these theoretical challenges, the basic concept of the event horizon as a point of no return remains robust. It is a direct consequence of general relativity, one of our most thoroughly tested scientific theories. For rotating black holes, described by the Kerr solution to Einstein's equations, the event horizon is not a perfect sphere, but an oblate spheroid, bulging at the equator due to the effects of rotation. These black holes have an additional region called the ergosphere, extending from the event horizon to a point where space-time is dragged around at the speed of light. Within the ergosphere, nothing can remain stationary relative to distant stars, as space-time itself is rotating. For charged black holes, described by the Reissner-Nordstrom solution for non-rotating charged black holes, or the Kerr-Newman solution for rotating charged ones, the structure becomes even more complex. These black holes can have two horizons, an outer event horizon and an inner Cauchy horizon. Between them lies a region where space-time has a different signature, meaning that the roles of time and space are altered in the mathematical description. Most black holes in nature are likely rotating, as they form from the collapse of rotating stars, or from the merger of objects with angular momentum. Astrophysical black holes are also likely to have negligible electric charge, as any significant charge would quickly be neutralized by attracting oppositely charged particles from the surroundings. The event horizon's existence has important implications for the ultimate fate of matter in the universe. If protons, the building blocks of atomic nuclei, are truly stable, as many physicists believe, then normal matter could in principle exist indefinitely. But in a universe with black holes, any matter that crosses an event horizon is, from the perspective of outside observers, removed from the normal universe and ultimately converted to Hawking radiation, as the black hole evaporates over unimaginably long timescales. From a philosophical perspective, the event horizon challenges our concepts of knowing and observing. We can never directly observe what happens beyond this boundary. Any theory about the interior of a black hole must be inferred from what we can observe from the outside and from the mathematical consistency of our physical theories. For someone crossing the event horizon, the experience would depend greatly on the size of the black hole. For a stellar mass black hole, tidal forces would tear apart any macroscopic object before it reached the horizon. But for a supermassive black hole, the tidal forces at the horizon itself could be quite mild, potentially allowing a human or even a spacecraft to cross intact. Once inside, the journey toward the singularity would have a finite duration from the traveler's perspective, typically on the order of seconds to minutes for a stellar mass black hole, longer for more massive ones. During this time, light from the outside universe would be visible, though distorted and concentrated in a shrinking patch of sky opposite the singularity. As the traveler approached the singularity, tidal forces would increase without bound. For any physical object, there would come a point where these forces exceeded the strength of even the strongest possible materials, leading to inevitable destruction. For an idealized point particle, the mathematics suggests arrival at the singularity itself, where space-time curvature becomes infinite, and our current physical theories break down completely. One of the most counterintuitive aspects of the event horizon is that, from the perspective of an outside observer, nothing ever quite crosses it. Due to the infinite time dilation at the horizon, objects approaching it appear to slow down and freeze there. Yet from the perspective of the falling object, the horizon is crossed in a finite and typically brief time. This seeming contradiction is resolved by recognizing that these are observations from different reference frames, and in the curved space-time near a black hole, there is no universal, absolute definition of simultaneity. For a distant observer, watching someone fall into a black hole, their image would appear to slow and redden as they approach the horizon. The light coming from them would be increasingly redshifted and dimmed, but some light would continue to arrive for a very long time, though eventually becoming too faint to detect. This leads to the poetic notion that, in a sense, the image of everything that has ever fallen into a black hole is still there, frozen at the horizon, fading but never quite gone. Recent observations have given us the first direct glimpses of the regions near event horizons. The Event Horizon Telescope, a global network of radio telescopes functioning as a single Earth-sized observatory, captured the first image of a black hole's shadow in 2019. This shadow is not the event horizon itself, which emits no light, but the dark region where light is either captured by the black hole or bent away from our line of sight. Another way we observe the effects of event horizons is through the properties of accretion disks, the swirling rings of gas and dust that often surround black holes. As matter in these disks spirals inward, it heats up due to friction and compression, emitting radiation across the electromagnetic spectrum. Just before this matter crosses the event horizon, it can release enormous amounts of energy, making quasars and active galactic nuclei some of the brightest objects in the universe. The detection of gravitational waves from merging black holes has provided yet another window on these enigmatic objects. The pattern of these waves carries information about the masses, spins, and other properties of the black holes before, during, and after the merger. The moment of merger itself, when the two event horizons combine to form a single larger one, produces a characteristic peak in the gravitational wave signal. For all its theoretical complexity, the concept of the event horizon has entered popular culture as a metaphor for a point of no return, a threshold beyond which familiar rules no longer apply. This reflects both the fascination these cosmic objects hold for the public imagination and the profound nature of the boundary they represent. In our journey into the heart of a black hole, crossing the event horizon represents a pivotal moment. It is the boundary between the universe we know, where communication with the outside is possible, and a region from which no message can ever be sent home. It is where space-time curves so severely that the very concept of outward direction ceases to exist. And yet, for all its cosmic significance, the event horizon is in a sense nothing at all. It is not a physical object, but a mathematical boundary, a set of points in space-time defined by a common destiny. It is invisible to those who cross it, detectable only through its effects on the surrounding universe and through the irreversible nature of the journey that follows. As we contemplate this cosmic boundary, we are reminded of how deeply unintuitive the universe can be at its extremes. The event horizon challenges our everyday understanding of space and time, forcing us to confront the malleability of these concepts in the context of extreme gravity. It stands as a monument to both the power of mathematical physics to describe the cosmos and the limits of our ability to directly observe and experience its most extreme regions. The event horizon awaits us on our journey, not as a wall to be breached, but as a one-way door to be passed through. Beyond it lies a region of space-time that, while governed by the same physical laws we know, arranges them in such a way that the familiar yields to the extraordinary. Beyond the event horizon, we enter a domain where all paths lead inward, where the singularity waits, not just as a point in space, but as an inevitable moment in time. You float through silence, stars fade, until there is nothing but the curve of infinity. Imagine a spaceship, specially designed for our impossible journey. It is shielded against radiation, reinforced against extreme tidal forces, equipped with instruments to measure the properties of space-time itself. We are about to embark on humanity's most daring voyage, an expedition to the edge of reality and beyond, as we approach a supermassive black hole. Why choose a supermassive black hole for our journey? The answer lies in the physics of tidal forces. If we were to approach a stellar mass black hole, the difference in gravitational pull between the nearest and farthest parts of our ship would become catastrophically large while we were still far from the event horizon. Our vessel would be stretched vertically and compressed horizontally, a process astronomers call spaghettification, named for the way it would elongate any object into a thin strand. No material known to science could withstand these forces. Even the strongest theoretical materials would fail. Atoms themselves would be torn apart, and eventually even subatomic particles would be stretched into their constituent quarks. Near a stellar mass black hole, spaghettification would destroy any macroscopic object long before it reached the event horizon. But supermassive black holes are different. The tidal forces at their event horizons are inversely proportional to the square of their mass. This means that the larger the black hole, the weaker the tidal forces at the horizon. For a black hole with a mass of about 100 million suns or more, a human could cross the event horizon without experiencing lethal tidal forces. This counterintuitive fact arises from the way gravity diminishes with distance. While the overall gravitational pull at the event horizon is stronger for more massive black holes, the gradient of the gravitational field, which causes tidal forces, is weaker. It's similar to the difference between a steep cliff and a gradual slope. Both might reach the same height, but the cliff represents a much more sudden change. For our journey, we choose a supermassive black hole with a mass of about 10 billion suns. One at the center of the galaxy, Messier 87, the first black hole ever to be directly imaged. Its event horizon has a radius of nearly 30 billion kilometers, about 200 times the distance from Earth to the Sun. The tidal forces at the horizon are mild enough that our reinforced spacecraft can withstand them. Our journey begins far from the black hole, in what astronomers call the asymptotically flat region of spacetime. Black holes' gravity are minimal. Here, space and time behave much as they do in other parts of the universe. Stars shine in recognizable constellations. The void of space stretches in all directions. The laws of physics operate in familiar ways. As we direct our spacecraft toward the black hole, the first thing we notice is the visible distortion of the starfield behind it. Stars that should be hidden behind the black hole from our perspective become visible, their light bent around the massive object by gravitational lensing. This effect, predicted by Einstein's general relativity and first confirmed during a solar eclipse in 1919, is dramatically enhanced around black holes. Stars near the apparent edge of the black hole stretch into arcs, creating partial or complete rings of light. This effect becomes more pronounced as we draw closer. Eventually, we begin to see multiple images of the same stars, their light taking different paths around the black hole to reach us. The black hole itself remains invisible, a dark absence against the twisted backdrop of stars. Our sensors detect the first hints of another phenomenon, the frame-dragging effect predicted by Austrian physicists Josef Lenzer and Hans Thirring in 1918. Space itself is being dragged around the rotating black hole, like honey swirling around a spinning spoon. This effect is subtle at first, but becomes increasingly significant as we approach. As we draw nearer, we begin to feel the first gentle tugs of tidal forces. The part of our ship closest to the black hole experiences slightly stronger gravity than the part furthest away. This creates a stretching sensation along the axis pointing toward the black hole and a compression perpendicular to this axis. Our ship's structural reinforcements easily compensate for these forces, which are still quite mild at this distance. We also begin to notice the effects of time dilation. Clocks on our ship tick slightly slower than those on Earth, a difference that will become increasingly dramatic as our journey continues. Communication with Earth becomes delayed, not just due to the increasing distance and the finite speed of light, but because time itself is flowing at different rates in the two locations. Now we approach what astronomers call the photon sphere, a region about 1.5 times the radius of the event horizon, where light can orbit the black hole in unstable circular paths. For our chosen supermassive black hole, this sphere has a radius of about 45 billion kilometers. If we were to emit a flash of light tangential to this sphere, it would orbit the black hole multiple times before either escaping to infinity or falling toward the event horizon. The visual distortions reach new extremes at this distance. Looking outward from the black hole, we see the entire universe compressed into a bright circle of light, with all the stars and galaxies visible at once. Looking toward the black hole, we see nothing but darkness, a perfect absence of light, surrounded by the increasingly distorted images of stars behind it. Our ship continues its approach, passing through the photon sphere and entering a region where the curvature of space-time becomes severe. Tidal forces increase but remain within the structural tolerances of our vessel. We begin to notice another effect, the gravitational blue shift of light from sources behind us. As this light falls toward the black hole with us, it gains energy and shifts toward the blue end of the spectrum, just as light climbing away from the black hole loses energy and redshifts. For a rotating black hole, which most astrophysical black holes are likely to be, we now enter a region called the ergosphere. This is not a physical structure but a region of space-time where the frame-dragging effect becomes so strong that nothing can remain stationary with respect to distant stars. Space itself is rotating faster than the speed of light relative to an outside observer, dragging everything within the ergosphere along with it. Within the ergosphere, we can still move in any direction and potentially escape the black hole, but we cannot resist the rotation. Our ship begins to orbit the black hole in the same direction as its rotation, even if we fire our engines in the opposite direction at full power. The ergosphere extends from the event horizon to a distance that depends on the black hole's rate of rotation, reaching its maximum extent at the black hole's equator and touching the event horizon at its poles. As we venture deeper into the ergosphere, closer to the event horizon, the rotation of space-time becomes more pronounced. We are moving not through static space, but through a dynamically rotating medium. It's as if we are trying to swim upstream in an increasingly powerful whirlpool, with the direction upstream becoming more and more aligned with the flow of the whirlpool itself. The tidal forces continue to strengthen, causing noticeable strain on our ship's structure. Automatic compensators adjust internal supports to counterbalance these forces. Our physicists confirm that the measurements match the predictions of general relativity precisely. The theory developed by Einstein over a century ago continues to accurately describe the behavior of spacetime, even in these extreme conditions. Our communication with Earth becomes increasingly redshifted and time-dilated. Messages we send take longer to arrive from Earth's perspective, while responses from Earth arrive at an accelerated pace from our point of view. This is not due to a change in the speed of light, which remains constant, but due to the different rates at which time flows in the curved spacetime near the black hole. Now we approach the event horizon itself, that critical boundary beyond which no return is possible. For our supermassive black hole, the event horizon is a sphere with a radius of 30 billion kilometers. But it is not a physical surface. There is no wall, no membrane, no barrier that we will feel as we cross. It is purely a mathematical boundary, defined by the fact that beyond this point, all possible future paths lead inward, toward the singularity. The visual distortions reach their peak as we near the horizon. The universe behind us is compressed into an increasingly small, bright circle, while the darkness ahead encompasses more and more of our field of view. Stars that were visible earlier now appear severely blue-shifted, their light gaining energy as it falls with us toward the black hole. Time dilation becomes extreme. Each second experienced on our ship corresponds to hours, then days, then years for observers on Earth. From their perspective, our approach to the event horizon appears to slow asymptotically, with our ship never quite reaching the horizon itself. Our image redshifts and dims, gradually fading from visibility. But from our perspective on the ship, time continues to flow normally. We cross the event horizon without experiencing any sudden change or discontinuity. There is no jolt, no flash of light, no dramatic indicator that we have passed a point of no return. The laws of physics continue to operate as they have throughout our journey. The looming darkness ahead and the shrinking circle of light behind are the only visual cues that we have entered a new regime. Yet something fundamental has changed. Before crossing the horizon, we could, at least in principle, reverse our course and return to Earth. Now, that option no longer exists. All possible future paths, regardless of how much energy we might expend, lead inexorably toward the singularity at the center of the black hole. It is not just that we cannot escape, but that the concept of escape, of moving outward away from the singularity, no longer has physical meaning. Inside the event horizon, the roles of space and time begin to shift. The radial coordinate, the distance toward the center of the black hole, takes on properties normally associated with time. Our movement toward the singularity becomes as inevitable as the forward flow of time itself. Just as we cannot avoid moving from Monday to Tuesday, we cannot avoid moving toward the singularity once inside the horizon. For a non-rotating black hole, this central singularity would be a point of infinite density and infinite space-time curvature. But for a rotating black hole, which our supermassive target almost certainly is, the singularity takes the form of a ring, a circle of infinite density in the equatorial plane of the black hole's rotation. This ring singularity has less extreme tidal forces in its vicinity than a point singularity, potentially allowing us to survive longer on our journey. As we continue inward, the tidal forces increase steadily. The structure of our ship creaks and groans under the strain. Warning lights illuminate as some systems approach their operational limits. Yet our reinforced hull continues to hold, at least for now. The supermassive nature of our chosen black hole means that these forces, while growing, increase gradually enough that we have time to experience and record the journey. Our instruments detect an interesting phenomenon predicted by general relativity. Inside the event horizon of a rotating black hole, there are regions where the extreme frame dragging effect makes it impossible to remain stationary with respect to the singularity. No matter how powerful our engines, we are dragged around the central ring in the direction of the black hole's rotation. This effect becomes more pronounced as we venture deeper. For a sufficiently rapidly rotating black hole, theoretical physics predicts the existence of an inner horizon, also called a Cauchy horizon. Unlike the outer event horizon, which is a point of no return for anything trying to leave the black hole, The inner horizon would be a boundary beyond which the deterministic nature of general relativity breaks down. Past this horizon, the theory suggests, multiple futures might become possible and the predictability of physical laws could be compromised. However, most physicists believe that in realistic black holes, the inner horizon would be unstable. The slightest perturbation, such as in falling matter or radiation, would cause it to become a region of infinite curvature, effectively a singularity itself. This phenomenon, known as mass inflation, would make the inner horizon as deadly as the central singularity. As our ship approaches the central regions of the black hole, the tidal forces finally become too great for our reinforced structure to withstand. Metal beams bend and twist, hull plates warp and crack. The internal compensators, designed to counterbalance tidal forces, reach their operational limits and begin to fail one by one. Our journey is about to end, not at the singularity itself, but at the point where the tidal forces exceed the structural integrity of our vessel. Before the ship breaks apart, we take final readings, capturing data that, in our thought experiment, might somehow be transmitted to the outside universe, providing insights into the extreme physics of black hole interiors. In the final moments, as the ship begins to disintegrate, we contemplate the remarkable journey we have undertaken. We have ventured where no human could actually go, crossing the boundary that separates the observable universe from a region of space-time that can never be seen from the outside. We have experienced the progressive warping of space and time as we approached and then crossed the event horizon. And we have gathered theoretical data on how matter behaves in the most extreme gravitational environment known to physics. Our physical forms are about to be reduced to their fundamental components by the tidal forces near the singularity. But in this thought experiment, we have gained invaluable insights into the nature of black holes, gravity, and the structure of space-time itself. This journey, impossible in reality but conceivable through the mathematics of general relativity, illuminates the profound and sometimes counterintuitive implications of Einstein's theory. It reminds us that black holes are not cosmic vacuum cleaners, indiscriminately sucking in everything around them, but regions of extremely curved space-time where the usual rules of space and time are transformed in ways that lead to the event horizon's defining characteristic, the impossibility of escape. For a real human or spacecraft approaching a black hole, the journey would differ in important ways from our thought experiment. The intense radiation from the hot accretion disk that typically surrounds black holes would likely prove fatal long before reaching the event horizon. The complex magnetic fields generated by swirling charged particles might tear apart any approaching object, and the practical challenges of navigating in such an extreme environment would be insurmountable with current or foreseeable technology. Yet the theoretical journey remains valuable. It helps us understand these extraordinary cosmic objects not as supernatural phenomena, but as natural consequences of the same physical laws that operate throughout the universe. It gives us a framework for interpreting the observational data we gather from safe distances, and it pushes us to confront the limits of our physical theories and to strive for deeper understanding. As our ship finally succumbs to the overwhelming tidal forces, breaking apart into its component atoms and eventually into subatomic particles, we reflect on what we have learned. We have seen that crossing the event horizon, while a point of no return, is not locally a dramatic event for the traveler. We have experienced the progressive warping of space-time as we ventured deeper into the black hole. And we have confirmed in our thought experiment that the predictions of general relativity continue to hold even in these extreme conditions. Our journey into a black hole, while imaginary, serves as a powerful tool for understanding these cosmic objects and the physics that governs them. It highlights the remarkable fact that the same theory that explains why apples fall from trees can also describe these most extreme objects in the universe. It reminds us of the unity of physical law, even in domains where our intuition fails us. And so our journey ends, not at the singularity itself, but on the way there, at the point where the tidal forces become too great for even our reinforced spacecraft to withstand. Yet in imagination, we have traveled farther than any human could actually go, crossing the boundary between the observable universe and a region from which no light, no information can ever return. We have begun a journey into the heart of a black hole, crossing the event horizon and experiencing the warped space-time within. As we continue our exploration in the chapters ahead, we will delve deeper into the theoretical implications of this journey, examining the nature of time distortion, the possibilities of exotic physics, and the ultimate fate of matter within these cosmic enigmas. We will venture in thought where no physical traveler could ever go, to the very edge of our understanding of the universe and perhaps beyond. You are not falling through space alone, you are falling through time. Time. It flows steadily forward, marking the progression of moments from past to future, the reliable backdrop against which all events unfold, or so it seems in our everyday experience. But Einstein's theories of relativity revealed a profound truth. Time is not absolute. It does not tick at the same rate for all observers. And nowhere is this more dramatically demonstrated than in the vicinity of a black hole. As we continue our theoretical journey deep into the gravitational well of a supermassive black hole, the nature of time itself becomes increasingly warped. What began as subtle effects, barely measurable differences in the ticking of clocks, grows into profound distortions that challenge our most basic intuitions about how reality operates. The time distortion near a black hole is not a different physical phenomenon from what we experience on Earth, merely an extreme version of it. Even on our home planet, time flows slightly more slowly at sea level than it does at the top of a mountain due to the difference in gravitational potential. GPS satellites must account for this effect, along with the effects of their orbital velocity, to maintain accurate timekeeping. Without these relativistic corrections, GPS positions would drift by about 10 kilometers each day. In everyday life, these effects are so small that we never notice them. The difference in the flow of time between your head and your feet is measurable only with the most precise atomic clocks. But near a black hole, these subtle effects become dramatic until they dominate the experience of anyone approaching the event horizon. In Einstein's theory of general relativity, gravity is not a force but a curvature of space-time caused by mass and energy. This curvature affects not just the paths that objects follow through space, but also the rate at which time flows. The stronger the gravitational field, the slower time passes relative to a distant observer in a weaker field. For a black hole, where the concentration of mass creates the strongest gravitational field possible, this time, dilation effect reaches its ultimate expression. At the event horizon itself, time dilation becomes infinite from the perspective of a distant observer. Someone watching from far away would see an approaching object appear to slow down, freeze, and redshift out of visibility as it neared the horizon. But for the person or object falling into the black hole, time continues to flow normally according to their own clocks and biological processes. They cross the event horizon without experiencing any sudden change or discontinuity in their experience of time. The dramatic differences in the flow of time only become apparent when comparing observations between the infalling observer and someone watching from a safe distance. This creates one of the most profound paradoxes of black hole physics. From the perspective of a distant observer, nothing ever quite reaches the event horizon. The infalling object appears to approach it asymptotically, slowing down more and more but never quite arriving, taking an infinite amount of time to reach the boundary. Yet from the perspective of the falling object, the horizon is crossed in a finite and typically brief amount of time. Both perspectives are correct within their own reference frames. There is no universal standard of simultaneity in the curved space-time around a black hole. Events that seem to occur at different times for one observer may appear simultaneous to another, and vice versa. This is not a matter of perception or optical illusion, but a fundamental property of how space-time behaves in strong gravitational fields. Imagine our spacecraft approaching the event horizon of our supermassive black hole. As we draw closer, each second that passes on our shipboard clocks corresponds to progressively longer periods for observers back on Earth. At first, the difference is minimal, with 1 second on our ship equating to perhaps 1.01 seconds on Earth. But as we approach the horizon, this difference grows exponentially. When we're very close to the horizon, a single second experienced on our ship might correspond to hours, then days, then years, and eventually centuries or millennia for distant observers. From their perspective, Our approach to the horizon appears to take forever, with our image freezing and reddening until it fades from visibility altogether. Yet for us on the ship, time flows without interruption. We cross the event horizon at a particular moment according to our clocks, experiencing no sudden change in the flow of time from our perspective. It is only by communicating with the outside world, an increasingly difficult proposition as we approach the horizon, that we would become aware of the extreme time dilation effects. This communication itself becomes affected by the time dilation. Messages we send become increasingly redshifted, their wavelengths stretched by the gravitational field, making them harder to detect. And the intervals between our transmissions, as measured by recipients far from the black hole, grow longer and longer, even if we send them at regular intervals according to our shipboard clocks. Conversely, signals we receive from the outside universe become increasingly blue-shifted, compressed into shorter wavelengths by their descent into the gravitational well, and they arrive at an accelerated pace from our perspective. We might receive what seems like years' worth of transmissions from Earth in the span of minutes according to our clocks. As we fall deeper into the black hole's gravitational influence, it's as if we're moving through time at a different rate than the rest of the universe. Near the event horizon, we would theoretically be able to witness the unfolding of cosmic events at a vastly accelerated pace. In the final moments before crossing the horizon, we might observe thousands or millions of years of galactic evolution in what seems to us like mere hours. Some physicists have speculated that this time dilation effect could, in theory, allow a civilization with sufficiently advanced technology to use the region near a black hole's event horizon as a form of time travel into the future. By spending what seems like a brief time in this region of extreme time dilation, they could return to find their homeworld aged by centuries or millennia. Of course, this would be a one-way trip into the future, with no possibility of return to their original time, and it would require careful station keeping to avoid being captured by the black hole, maintaining position in a region of extreme but not infinite time dilation, where the tidal forces had not yet become destructive. The engineering challenges would be immense, far beyond our current capabilities, but the physics does not forbid such a possibility. Once we cross the event horizon, the time distortion effects become even more profound. Inside the horizon, the roles of space and time begin to shift in the mathematical description of space-time. The radial coordinate, measuring the distance to the center of the black hole, takes on properties normally associated with time. Our movement toward the singularity becomes as inevitable as the forward flow of time itself. This inversion of roles between space and time is difficult to visualize, but can be expressed mathematically in the solutions to Einstein's field equations that describe a black hole's spacetime. Inside the horizon, all future light cones, the paths that light and therefore all causally connected events can take, point toward the singularity. The direction outward, away from the singularity, is no longer available as a path through time, just as the past is no longer available to us in normal spacetime. For a non-rotating black hole, this singularity lies in our unavoidable future, a moment when space-time curvature becomes infinite and our current understanding of physics breaks down. For a rotating black hole, the situation is more complex, with the possibility of avoiding the ring singularity and perhaps encountering an inner Cauchy horizon, though many physicists believe this inner horizon would be unstable and effectively singular in realistic scenarios. The time distortion effects near a black hole highlight the relational nature of time in Einstein's theory. There is no universal clock ticking at the same rate throughout the universe. Time is a local phenomenon, flowing at different rates depending on the gravitational potential and the relative motion of observers. This leads to another counterintuitive aspect of black hole physics, the black hole information paradox. When matter falls into a black hole, detailed information about its state seems to be lost from the universe, as no signal can emerge from beyond the event horizon. Yet quantum mechanics insists that information cannot be truly destroyed. This apparent contradiction points to a deeper tension between our two most successful physical theories, general relativity and quantum mechanics. Stephen Hawking's discovery that black holes emit radiation, now called Hawking radiation, suggested a possible resolution to this paradox. This radiation causes black holes to slowly lose mass and eventually evaporate completely. The question of whether and how this radiation carries information about what fell into the black hole remains an active area of research at the frontier of theoretical physics. The holographic principle, developed by Gerard T. Hooft, Leonard Susskind, and others, offers another perspective on this paradox. It suggests that all the information about matter that falls into a black hole is somehow encoded on the event horizon. This principle has broader implications, suggesting that the information content of any region of space can be represented on the boundary of that region, with the volume description and the boundary description being different but equivalent ways of representing the same physics. As we contemplate these profound distortions of time near a black hole, we begin to see why these cosmic objects have captured the imagination of both scientists and the public. They are not just destructive cosmic vacuum cleaners, but laboratories for exploring the deepest aspects of reality, regions where the malleability of time becomes undeniable and where our most successful theories approach or perhaps reach their limits. For anyone falling into a black hole, the experience would be a journey not just through space, but through time itself, experiencing temporal effects that have no parallel in ordinary human experience. It would be a one-way journey, with no possibility of return, into a region where time flows at a rate profoundly disconnected from the rest of the universe. Near the event horizon, time stretches and bends to its breaking point. What seems like moments to the infalling observer corresponds to an eternity for the outside universe. The horizon itself marks a boundary, not just in space but in time, a division between regions where different laws of temporal progression apply. Inside the horizon, as we continue our theoretical journey deeper into the black hole, the inevitability of our progress toward the singularity mirrors the inevitability of time's forward flow in normal spacetime. We cannot avoid moving toward the singularity any more than we can avoid moving from the present into the future outside a black hole. The direction of time itself has been warped and redefined by the extreme curvature of spacetime. Our journey through a black hole is as much a journey through time as it is through space, a passage through regions where these two aspects of reality interchange roles and where our ordinary understanding of temporal progression breaks down. It is a stark reminder that time is not what our everyday experience suggests, a steady, universal flow from past to future, but a dynamic aspect of a unified spacetime, subject to warping and distortion in the presence of mass and energy. As we fall deeper into the gravitational well, time's arrow bends ever more sharply until it points inevitably toward the singularity. Our journey continues, not just through the curved space of the black hole's interior, but through a twisted time, stretched and compressed in ways that defy ordinary understanding, but follow with mathematical precision from the principles of relativity. We are not just falling through space, we are falling through time itself, experiencing directly what Einstein's equations tell us must be true, that time is not absolute but relative, not fixed but malleable, not universal but local. In the depths of a black hole, these abstract principles become concrete realities, shaping our experience in profound and inescapable ways. And so we continue our descent, moving not just toward the center of the black hole, but toward the limits of our understanding of time and space, toward a singularity that represents not just a point in space, but a moment in time where our current physical theories reach their breaking point. It is a journey not just through the most extreme environment known to physics, but through the very fabric of temporal reality, warped and stretched to its ultimate limits by the immense gravitational field of the black hole. Time dilation, from a subtle effect barely noticeable in everyday life, has become the dominant aspect of our experience. The disconnect between our temporal reference frame and that of the universe outside the black hole is now complete. We have entered a domain where time flows according to different rules, a region causally separated from the rest of the cosmos, where the ordinary progression of moments has been fundamentally altered by the extreme curvature of space-time. Beyond the known lies the unknowable, but we must imagine if we are to journey on. We have crossed the event horizon in our theoretical journey, entering a region from which no information can ever escape back to the universe outside. We are now in truly uncharted territory, not just practically unexplored, but fundamentally unexplorable from the perspective of external observers. Inside the event horizon, we encounter physics at the very edge of our understanding, where our best theories begin to strain and possibly break down. General relativity, Einstein's theory of gravity as curved spacetime, provides a mathematical description of what should happen inside a black hole. Quantum mechanics, our theory of the very small, offers insights into how matter and energy behave at subatomic scales. Yet these two pillars of modern physics, each extraordinarily successful in its domain, have not been fully reconciled. Inside a black hole, where extreme gravity meets the quantum realm, their uneasy coexistence becomes a pressing theoretical problem. According to general relativity alone, the interior of a black hole has a well-defined structure. For a non-rotating black hole, described by the Schwarzschild solution to Einstein's field equations, the singularity at the center is a point of infinite density and infinite space-time curvature. All infalling matter and energy are inexorably drawn toward this point, where the known laws of physics break down. For a rotating black hole, described by the Kerr solution, the central singularity takes the form of a ring rather than a point, spinning rapidly in the equatorial plane. This ring singularity has the peculiar mathematical property that it can, in principle, be avoided. An object falling into a rotating black hole might, according to the mathematics, pass through the ring without encountering infinite curvature and emerge into a region with unusual properties. But general relativity, for all its success in describing gravity and spacetime, does not incorporate quantum effects, which must become significant near the singularity. The theory predicts its own breakdown, yielding infinite values for key physical quantities, a sign that it has reached the limits of its applicability. When a physical theory predicts infinities, it is usually a sign that the theory is being pushed beyond its domain of validity. Quantum mechanics, meanwhile, tells us that at very small scales, reality becomes probabilistic rather than deterministic. Particles can exist in multiple states simultaneously until measured. Energy can fluctuate spontaneously out of the vacuum. Space itself becomes a seething foam of virtual particles popping in and out of existence. These quantum effects must play a role in the physics of the black hole interior, especially near the singularity, but exactly how remains a subject of intensive theoretical research. The quest to unify general relativity and quantum mechanics, to create a theory of quantum gravity that would apply in regions of extreme spacetime curvature like the interior of a black hole, has occupied some of the finest minds in physics for decades. Several approaches have been developed, including string theory, loop quantum gravity, and others, each with its own mathematical framework and physical implications. String theory suggests that what we perceive as fundamental particles are actually tiny, one-dimensional strings vibrating in multiple dimensions. In this framework, the singularity at the center of a black hole might be resolved, replaced by a region where the fundamental strings exist in a highly excited state. The infinity predicted by general relativity would be an artifact of treating particles as point-like objects when they are actually extended entities. Loop quantum gravity, another approach to quantum gravity, suggests that spacetime itself has a discrete granular structure at the smallest scales, rather than being a smooth continuum. In this theory, the singularity might be avoided because there is a minimum size to the quanta of space. The apparently infinite curvature at the singularity would be limited by the discrete nature of spacetime itself. These theories and others offer tantalizing glimpses of what might lie at the heart of a black hole, but none has been definitively confirmed by observation or experiment. The interior of a black hole remains one of the greatest mysteries in physics, a region where our best theories reach their limits and possibly break down entirely. One intriguing possibility is that the center of a black hole might not contain a singularity at all, but rather some exotic state of matter or energy that current physics cannot fully describe. Some theoretical work suggests that matter falling into a black hole might reach a state of maximum density allowed by quantum mechanics, forming what has been called a Planck star or a fuzzball, depending on the theoretical approach. In these scenarios, the black hole interior would not contain a point or ring of infinite density, but a region where matter has been compressed to the maximum extent allowed by the laws of quantum physics. This would avoid the troubling infinities predicted by classical general relativity, while still accounting for the extreme gravitational effects observed from outside. Another possibility is that the interior of a black hole might contain a region of space-time with properties very different from those outside. Some solutions to Einstein's equations suggest the possibility of what physicists call a white hole, a theoretical entity that is, in a sense, the opposite of a black hole. While nothing can escape from a black hole, nothing can enter a white hole. It can only emit matter and energy. In some theoretical frameworks, black holes and white holes might be connected, forming a structure called an Einstein-Rosen bridge, or more colloquially, a wormhole. Such a structure might connect two distant regions of our universe, or even link our universe to another. However, most analyses suggest that such connections would not be traversable by physical objects or information, at least not without the presence of exotic matter with negative energy density, which may not exist in nature. The Cauchy horizon, a theoretical boundary inside a rotating black hole, is another region where physics becomes particularly strange. Beyond this horizon, general relativity suggests that causality itself breaks down. Events in one region can influence their own past, creating causal loops that violate our ordinary understanding of cause and effect. However, most theoretical physicists believe that the Cauchy horizon would be unstable in realistic black holes. Any perturbation, such as infalling matter or radiation, would cause the Cauchy horizon to become a singularity itself, a phenomenon known as mass inflation. This would prevent the formation of causal paradoxes, but would also mean that any infalling observer would encounter a singularity before reaching regions where causality breaks down. The black hole information paradox, first identified by Stephen Hawking, represents another profound challenge to our understanding of physics inside and around black holes. Quantum mechanics requires that information about the state of a system cannot be destroyed, only transformed. Yet black holes appear to destroy information when matter falls in, as all details about the infalling matter, aside from its mass, angular momentum, and electric charge, seem to be erased from the universe. Hawking's discovery that black holes emit radiation, now called Hawking radiation, suggested a possible resolution to this paradox. This radiation, produced by quantum effects near the event horizon, causes black holes to slowly lose mass and eventually evaporate completely. But the question remains, does this radiation carry information about what fell into the black hole? And if so, how is this information encoded? The debate over the black hole information paradox has led to profound insights and continues to drive theoretical research. Proposed resolutions include the possibility that information is stored on the event horizon itself, in line with the holographic principle, or that the radiation somehow encodes information about the black hole's interior in subtle quantum correlations. Another approach, the firewall hypothesis, suggests that the conflict between general relativity and quantum mechanics leads to a dramatic breakdown of space-time at the event horizon itself. In this scenario, an infalling observer would encounter not the smooth boundary predicted by general relativity, but a high-energy region, a firewall that would destroy any object crossing it. This would preserve the principles of quantum mechanics, but would require modifying our understanding of what happens at the event horizon. Other theories propose that the interior of a black hole might be much more complex than classical general relativity suggests. Instead of a simple progression toward a singularity, the interior might contain regions of highly curved but non-singular spacetime, perhaps even with distinct regions that in some sense replicate the information content of everything that fell in. The fuzzball proposal, developed within string theory, suggests that black holes are actually complex, horizon-sized quantum objects with no interior or singularity in the conventional sense. According to this idea, the information about whatever falls into a black hole is stored in subtle quantum modifications to the horizon itself, preserving information without requiring it to escape from behind the event horizon. The ER equals EPR conjecture, proposed by physicists Leonard Susskind and Juan Maldacena, suggests a deep connection between quantum entanglement, a phenomenon where particles remain correlated regardless of distance, and wormholes connecting different regions of spacetime. This provocative idea hints at ways that quantum information might be preserved in black holes through connections that transcend ordinary spatial relationships. Some researchers have even proposed that the interior of a black hole might contain an entire new universe, expanding from what appears to us as a singularity. In this scenario, what we perceive as a black hole might be the Big Bang of another cosmos, with our observable universe potentially having originated as a black hole in some larger structure. While speculative, such ideas highlight the profound connections between black hole physics and cosmology. As we theoretically continue our journey deeper into the black hole, we are venturing into realms where different possibilities branch out from our known physics. Some theories suggest we would encounter a singularity, perhaps softened by quantum effects, but still marking the end of our journey and possibly the end of space-time as we understand it. Others propose more exotic possibilities, regions where space-time takes on fundamentally different characteristics, or where new dimensions might become apparent. What seems certain is that inside a black hole, at least in some regions, our familiar notions of space and time undergo radical transformations. The usual spatial direction toward the center of the black hole takes on aspects normally associated with the forward flow of time, making progress toward the center as inevitable as the passage of moments. Space and time themselves may dissolve into more fundamental entities, perhaps the vibrations of strings or the loops of quantum geometry, from which our familiar four-dimensional space-time emerges only as a large-scale approximation. The unknown physics of the black hole interior represents one of the greatest frontiers in theoretical physics. It is a domain where our most successful theories meet their limits, where infinities appear in our equations, and where even basic concepts like causality and the nature of information are called into question. It is precisely because of these challenges that black holes have become such a focus of theoretical research, serving as laboratories for exploring the most fundamental aspects of physical reality. For our imaginary journey, the implications are profound. As we descend deeper into the black hole, we are not just exploring an extreme environment within known physics. We are venturing into territory where physics itself begins to transform, where new principles may emerge, and where our most basic concepts may require revision or replacement. The tidal forces, which have been steadily increasing throughout our descent, would eventually become strong enough to overcome any material strength, tearing apart any macroscopic object. But even this process would be governed by physics we only partially understand, as quantum effects become increasingly important at the subatomic scales to which we would ultimately be reduced. In the final approach to the singularity, if indeed a singularity awaits us, we would encounter conditions where known physics simply cannot provide a complete description. Quantum fluctuations would become so significant that the classical concept of a smooth space-time might break down entirely. We might enter a realm where space and time themselves are emergent rather than fundamental, arising from deeper structures that our current theories only hint at. The journey into a black hole is thus not just a journey to an extreme environment, but a journey toward the frontiers of knowledge itself. It is a theoretical exploration of domains where our best understanding begins to fray, and where new physics, perhaps radically different from what we currently know, must come into play. It is a journey into the unknown, guided by mathematics and theory, but ultimately leading to regions where speculation must supplement what we can derive with confidence. As we contemplate these possibilities, we're reminded of the remarkable reach of human understanding. Through mathematics and physical theory, we can meaningfully discuss regions of reality that no human will ever directly observe, regions sealed off from the rest of the universe by the event horizon. Yet we can also recognize the limits of our knowledge, the points where our theories break down, and where new ideas will be needed to proceed further. The black hole interior represents both the power and the limitations of science. It shows how far we can extend our understanding through the tools of mathematics and theoretical physics. And it reminds us that there are still deep mysteries at the heart of reality, regions where our current understanding is incomplete and where future discoveries await. As our theoretical journey continues, we venture into these unknowns, guided by our best current theories, but prepared to encounter phenomena that may transcend our present understanding. We are explorers at the frontier of knowledge, venturing not just into the extreme environment of a black hole, but into the domain where physics itself transforms and evolves. Perhaps you do not die at the center. Perhaps you arrive. The concept of a wormhole, a theoretical passage through space-time that could create shortcuts for long journeys across the universe, has captured the imagination of scientists and science fiction enthusiasts alike. But what exactly are wormholes? How might they relate to black holes? And could they possibly offer a means of survival for someone falling into a black hole? Let us explore these fascinating possibilities. The story of wormholes begins in 1916, just months after Albert Einstein published his general theory of relativity. Physicist Ludwig Flamm, examining Karl Schwarzschild's solution to Einstein's field equations, noticed that the mathematics seemed to describe not just one universe, but two, connected by a narrow throat or tunnel. This was the first hint that Einstein's theory might allow for passages between different regions of space-time. In 1935, Einstein himself, working with physicist Nathan Rosen, explored this idea further. They discovered that the Schwarzschild solution, which describes the space-time around a non-rotating black hole, contains a feature that would later become known as an Einstein-Rosen bridge. This theoretical structure would connect two separate regions of space-time, either two different parts of our universe, or perhaps our universe and another. The term wormhole was coined much later, in 1957, by physicist John Wheeler. The name evokes the idea of a worm tunneling through an apple, creating a shortcut between 2 points on the surface by traveling through the interior. Similarly, a wormhole would provide a shortcut through space-time, potentially allowing travel between distant regions in less time than light would take to make the journey through normal space. In the simplest conception, a wormhole might connect the interior of a black hole to a white hole. While a black hole allows matter and energy to flow in but not out, a white hole would allow matter and energy to flow out but not in. The white hole would essentially be the time reversal of a black hole, ejecting matter and radiation instead of consuming it. The Einstein-Rosen bridge, in its original form, is not traversable. The throat of the wormhole contracts so quickly that nothing, not even light, can pass through it from one side to the other. Any attempt to enter the wormhole from the black hole side would lead inevitably to the singularity, not to an exit through a white hole. However, in 1988, physicists Kip Thorne and his colleagues discovered that if a form of negative energy or negative mass could be used to hold the throat open, a traversable wormhole might be theoretically possible. Such a wormhole would allow for two-way travel between its mouths, potentially enabling journeys across vast cosmic distances in short periods of time. Negative energy might sound like pure science fiction, but quantum mechanics suggests that it can exist in limited forms. The Casimir effect, for instance, creates a small region of negative energy density between two closely spaced parallel plates. However, the amount of negative energy that can be created through known physical processes falls far short of what would be needed to hold open a macroscopic wormhole. For our theoretical journey into a black hole, the possibility of a wormhole offers an intriguing alternative to the grim fate of encountering a singularity. If our black hole were somehow connected to a white hole elsewhere through a traversable wormhole, we might, in principle, emerge in another region of our universe, or even in another universe entirely. But there are significant obstacles to this scenario. First, there is no observational evidence that traversable wormholes exist in nature. They are allowed by the mathematics of general relativity under certain conditions, but that doesn't mean they actually form in the real universe. Second, even if wormholes do form naturally, they would likely be microscopic and would collapse too quickly for anything to pass through unless stabilized by exotic matter with negative energy density. The physics of rotating black holes, described by the Kerr solution to Einstein's equations, offers another intriguing possibility. In the mathematical model of a maximally rotating black hole, an infalling object might avoid the ring singularity and emerge into another region of space-time, sometimes called a different universe or a different branch of our universe. These mathematical solutions suggest the possibility of closed time-like curves, paths through space-time that return to their starting point in time as well as space. In principle, such paths would allow for time travel, raising the specter of paradoxes like the famous grandfather paradox, where a time traveler might prevent their own birth by interfering with their ancestors. Most physicists believe that some principle, perhaps yet undiscovered, would prevent the formation of closed time-like curves and the paradoxes they would entail. Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics somehow conspire to prevent time travel and thereby protect the consistency of causality. Another possibility is that wormholes, if they exist, might connect our universe not to another region of the same space-time, but to another universe entirely, with potentially different physical laws and constants. This idea has been explored in various multiverse theories, which suggest that our universe might be just one of many, each with its own distinct characteristics. The many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957, suggests that every quantum event creates a branching of reality into multiple universes, each representing a different outcome. Some speculative theories have proposed that black holes might serve as bridges between these parallel universes, though there is currently no experimental evidence for this idea. For our theoretical journey, these possibilities offer a more optimistic alternative to the scenario where we inevitably encounter a singularity. Perhaps, instead of being destroyed by infinite tidal forces, we might pass through a wormhole within the black hole and emerge elsewhere, or even elsewhen. But we must be clear about the speculative nature of this scenario. While wormholes are mathematical solutions to Einstein's equations, there is no observational evidence that they exist in the actual universe. And even if they do exist, they would likely require exotic matter or energy configurations to remain open long enough for anything to pass through. The concept of wormholes has been further developed in theoretical physics through models like the ER equals EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind. This idea suggests a deep connection between quantum entanglement, where particles remain correlated regardless of distance, and wormholes connecting different regions of spacetime. In this framework, entangled particles might be connected by a kind of quantum wormhole, too small for matter to traverse, but potentially allowing for a form of information connection across spacetime. This provocative idea represents an attempt to bridge quantum mechanics and general relativity, two pillars of modern physics that have proven difficult to reconcile. Another approach to wormhole physics comes from string theory, which suggests that our universe might have extraspatial dimensions beyond the three we experience directly. In some string theory models, what appears to us as a black hole might be a tunnel to these extra dimensions or to other branes, three-dimensional universes existing within a higher dimensional space. These theoretical approaches highlight the breadth of possibilities being explored at the frontiers of physics. While we have no direct evidence for wormholes, extra dimensions, or connections between black holes and other universes, these ideas emerge naturally from our attempts to develop a more complete understanding of fundamental physics. For someone falling into a black hole, the likelihood of encountering a traversable wormhole rather than a destructive singularity remains vanishingly small based on our current understanding. But the mathematical possibility exists, and in the extreme environment of a black hole's interior, where our best physical theories begin to break down, we cannot completely rule out exotic possibilities. If, against all odds, our journey through a black hole did lead us through a wormhole, what might we experience? Theoretical models suggest a passage through a tunnel-like structure, with significant tidal forces, but perhaps not the infinite stretching and compression associated with a singularity. At the other end, we might emerge from a white hole into another region of space-time, perhaps another part of our universe, or perhaps something even more exotic. The visual experience of such a passage is difficult to predict with certainty, but it might involve severe optical distortions as light follows the curved geometry of the wormhole. We might see multiple distorted images of the space ahead of and behind us, with strange patterns of blue-shifted and red-shifted light, depending on the precise geometry of the passage. From an engineering perspective, even if traversable wormholes are theoretically possible, creating or stabilizing one would require technological capabilities far beyond anything currently available or foreseeable. The amount of negative energy needed to keep a macroscopic wormhole open would be enormous, and we currently have no way to generate such quantities. Some speculative proposals have suggested that an advanced civilization might be able to capture a naturally occurring microscopic wormhole and somehow enlarge it using negative energy. Others have proposed that exotic quantum effects near the Planck scale, where space-time itself might have a discrete, foam-like structure, could potentially be harnessed to create wormhole connections. But these remain highly speculative ideas, far from anything we could currently implement or even fully analyze with our existing theories. Another intriguing possibility comes from certain models of the early universe. Some theories suggest that microscopic wormholes might have formed naturally during the inflationary period, shortly after the Big Bang, when space-time was expanding at an exponential rate. If any of these primordial wormholes survived to the present day and somehow grew or were stabilized, they might provide natural tunnels through space-time. The possibility of using wormholes for interstellar travel has been a staple of science fiction for decades. Indeed, the concept offers a potential workaround to one of the most significant obstacles to exploring the galaxy: the vast distances between stars and the cosmic speed limit imposed by the speed of light. If stable, traversable wormholes could be created or found, they might allow for journeys between star systems in reasonable amounts of time, without requiring faster-than-light travel through normal space. But there are significant complications, even in this theoretical scenario. Wormholes, if they exist, might connect random points in space-time rather than convenient destinations. The forces within them might be too extreme for any physical object or living being to survive passage, and the exotic matter required to keep them open might have other unpredictable or dangerous properties. From a cosmological perspective, the existence of traversable wormholes would have profound implications. They would effectively create shortcuts in the causal structure of the universe, potentially allowing for communication or even travel between regions that would otherwise be causally disconnected due to the expansion of space and the finite speed of light. This raises interesting questions about the ultimate fate of intelligent life in an expanding universe. If wormholes cannot exist or cannot be stabilized, then the accelerating expansion of space will eventually isolate galaxies from one another, creating a cosmic horizon beyond which no information can be exchanged. But if traversable wormholes are possible, they might provide a means to maintain connections across these ever-increasing distances. The connection between black holes and wormholes highlights the remarkable richness of Einstein's general theory of relativity. A theory developed primarily to explain gravity has yielded insights into the possible structure of spacetime itself, suggesting exotic geometries that might allow for journeys across the cosmos or even between universes. Yet we must maintain a clear distinction between what the mathematics allows and what observational evidence supports. Wormholes emerge naturally from certain solutions to Einstein's field equations, but we have no direct evidence that they exist in the actual universe. They represent a fascinating possibility allowed by our best theory of spacetime, but not yet confirmed by observation. For our theoretical journey into a black hole, wormholes offer a tantalizing alternative to the seemingly inevitable destruction at a singularity. They suggest that what appears to be the end might actually be a passage, that what seems like death might actually be transformation or transit to somewhere else. This possibility resonates with mythological and religious conceptions of death as a transition rather than an ending, of boundaries as passages rather than absolute limits. Perhaps this is why wormholes have captured the public imagination so strongly, reflecting our hope that even the most absolute boundaries might contain hidden doorways. But we must approach such possibilities with scientific rigor, recognizing that while wormholes are mathematically allowed under certain conditions, their existence in the actual universe remains speculative. The journey to the center of a black hole most likely leads not to another universe, but to conditions where our current understanding of physics breaks down entirely. The Einstein-Rosen bridge and its more traversable cousins remind us of how much we still have to learn about the fundamental nature of spacetime. They suggest possibilities that, while perhaps not realized in our universe, help us explore the full implications of our physical theories. They stand at the boundary between established science and speculative physics, between what we know and what we can only imagine. As we continue our theoretical journey deeper into the black hole, we hold open the possibility, however remote, that we might encounter not just the end of our existence, but a passage to somewhere new. We acknowledge the slim chance that instead of being destroyed at a singularity, we might emerge elsewhere, transformed but intact. We consider that perhaps, as the chapter title suggests, we do not die at the center, but arrive. To die in a black hole may not be death as we know it. It may be rebirth in an unrecognizable form. As we continue our theoretical journey deeper into a black hole, we approach the ultimate question: what happens to matter, to information, to consciousness itself in the most extreme environment known to physics? Is the end result inevitably destruction, or might there be some form of transformation, a change so profound that it transcends our ordinary categories of existence and non-existence? We have seen that the fate of an object falling into a black hole depends greatly on the black hole's mass. For stellar mass black holes, with masses ranging from a few to a few tens of times that of our Sun, the tidal forces near the event horizon are catastrophic. Any macroscopic object, whether a spacecraft, a human body, or even a molecule, would be stretched and compressed with such violence that no known material could maintain its integrity. This process of spaghettification would reduce the object to a stream of elementary particles long before it reached the central singularity. But for supermassive black holes, with masses millions or billions of times that of our Sun, the tidal forces at the event horizon can be surprisingly mild. An astronaut crossing the horizon of such a black hole might not notice anything unusual at that moment, experiencing no sudden increase in the stretching forces. The fatal tidal forces would come later, as they approached the central regions, where space-time curvature becomes extreme. In either case, conventional wisdom in physics suggests that any object falling into a black hole will eventually be destroyed. The tidal forces grow without bound as the object approaches the singularity, eventually exceeding the strength of any known or theoretical material, tearing apart atoms, nuclei, and eventually elementary particles themselves. This destruction is not just the breaking of bonds between particles, but a fundamental transformation of the infalling matter. As it approaches the singularity, matter encounters conditions where our current physical theories break down, where space-time curvature approaches infinity, and where quantum effects must become significant but are not fully described by our existing theories. Yet destruction may not be the end of the story. In physics, we know that matter and energy cannot be truly destroyed, only transformed. The first law of thermodynamics, the conservation of energy, remains one of our most fundamental principles. Even in a black hole, this principle should still apply, though perhaps in ways we do not yet fully understand. So what happens to the energy, the mass, the information contained in an object that falls into a black hole? This question leads us to one of the most profound puzzles in theoretical physics, the black hole information paradox, first identified by Stephen Hawking in the 1970s. Hawking's analysis combined quantum field theory with general relativity and led to the remarkable discovery that black holes are not completely black. They emit a form of radiation, now called Hawking radiation, produced through quantum effects near the event horizon. This radiation causes black holes to slowly lose mass and eventually to evaporate completely. But this discovery created a paradox. According to quantum mechanics, information about physical systems cannot be destroyed. Yet Hawking's initial calculations suggested that the radiation emitted by a black hole contained no information about what had fallen in. It seemed that when a black hole finally evaporated, all the detailed information about what had formed it or fallen into it would be permanently lost from the universe. This apparent destruction of information created a fundamental conflict between quantum mechanics and general relativity. Quantum mechanics insists that information must be preserved, while general relativity, combined with quantum field theory in curved spacetime, seem to allow information to be lost in black holes. Over the decades since Hawking's initial work, theoretical physicists have proposed various resolutions to this paradox. One approach suggests that the information is preserved in subtle quantum correlations within the Hawking radiation. While each individual particle of radiation might appear random and unrelated to what fell in, the pattern of all radiation emitted over the black hole's lifetime might encode all the information about its formation and everything that fell into it. Another approach developed within string theory, is the holographic principle. This suggests that all the information about what falls into a black hole is somehow encoded on the event horizon itself. The three-dimensional contents of the black hole would be completely described by a two-dimensional theory on its boundary. This counterintuitive idea has found support in certain mathematical relationships between gravitational theories and quantum field theories, particularly the ADS-CFT correspondence discovered by Juan Maldacena. A more radical proposal is that the information is preserved because infalling matter never actually crosses the event horizon, at least from the perspective of external observers. Due to the extreme time dilation near the horizon, outside observers would see infalling matter appear to slow down and freeze just above the horizon. Some theories suggest that the matter would then be scrambled and redisseminated back to the universe through the Hawking radiation process, thus preserving the information. Yet another possibility is that the singularity at the center of the black hole is not a point where physics breaks down completely, but a transition to another region of space-time, or perhaps another universe entirely. In this scenario, information would not be destroyed, but would pass through to this other domain, inaccessible to observers in our universe, but still existing in a broader sense. These various proposals highlight a profound insight that what appears as destruction from one perspective might be transformation from another. An object falling into a black hole might be destroyed as a coherent entity with a specific structure, but the energy, the mass, and perhaps even the information contained within it might persist in a transformed state. The fate of consciousness in a black hole presents an even more profound mystery. If a conscious being were to fall into a black hole, what would happen to their subjective experience? Would consciousness simply cease at the moment when the brain's physical structure was destroyed by tidal forces? Or might there be some sense in which a transformed version of that consciousness could persist? This question takes us beyond physics into philosophy and the nature of consciousness itself. If consciousness is entirely a product of the physical structure and activity of the brain, then its destruction would presumably end consciousness. But if consciousness has aspects that transcend its particular physical implementation, there might be theoretical possibilities for its continuation in some form. Some philosophers and theoretical physicists have explored speculative ideas about consciousness as a fundamental aspect of the universe, not reducible to purely physical processes. Such approaches might suggest possibilities for the transformation, rather than the simple destruction of consciousness in a black hole. But these remain highly speculative ideas, far from the mainstream of current scientific understanding. From a more conventional scientific perspective, the death of an object or person in a black hole seems inevitable. The extreme tidal forces would destroy any physical structure, including a brain, long before reaching the singularity. Any subjective experience dependent on that physical structure would presumably end at that point. Yet even this destruction is not simple annihilation. The matter that comprised the object or person would not cease to exist, but would be transformed, initially into a stream of elementary particles, and eventually into conditions where our current physics cannot provide a complete description. The energy and information contained in that matter would be preserved in some form, though perhaps encoded in ways we do not yet fully understand. This transformation extends beyond the fate of individual objects to the ultimate fate of black holes themselves. According to Hawking's analysis, black holes are not eternal, but slowly evaporate through the emission of radiation. A stellar mass black hole would take on the order of 10 to the power of 67 years to evaporate completely, far longer than the current age of the universe. But eventually, all black holes will dissipate, returning their mass energy to the universe in the form of radiation. This process represents a kind of cosmic recycling, where matter that falls into a black hole is not permanently removed from the universe, but is ultimately returned, albeit in a completely transformed state. The structured matter that fell in, whether stars or planets or living beings, would be reduced to elementary particles and radiation, losing all its original organization, but conserving the fundamental quantities of energy, momentum, and possibly information. The question of what happens at the final stages of black hole evaporation remains an open area of research. As a black hole loses mass, its temperature increases and the rate of evaporation accelerates. In the final moments, as the black hole approaches the Planck mass, about 22 micrograms, it would emit radiation at enormous temperatures. At this scale, a full quantum theory of gravity would be needed to describe what happens, and our current theories are incomplete. Some theories suggest that the black hole might evaporate completely, leaving behind only radiation. Others propose that a stable remnant might remain, a Planck-scale object containing all the information about what formed the black hole and what fell into it. Still others suggest more exotic possibilities, such as a transition to a baby universe or a burst of matter through a white hole. These various possibilities highlight how the apparent death of matter in a black hole might actually be part of a larger cycle of transformation. Matter falls into a black hole, is reduced to its elementary components, and may ultimately be returned to the universe in a different form. Black holes themselves form, grow, and eventually evaporate, participating in the ongoing processes of cosmic evolution. From this perspective, black holes may be less about endings than about transformations, less about death than about change so profound that it transcends our ordinary categories. They represent environments where the familiar structures of matter cannot survive, but where the fundamental components of reality endure, albeit in radically different configurations. This view resonates with perspectives from various philosophical and spiritual traditions, which often see death not as a final end, but as a transformation or transition. The scientific perspective does not validate any particular metaphysical belief about consciousness or the afterlife, but it does suggest that even in the most extreme environments known to physics, the fundamental constituents of reality are preserved, even as their organization is radically altered. For our theoretical journey into a black hole, this suggests a nuanced understanding of the fate that awaits us. Our physical forms would certainly be destroyed by the extreme tidal forces. The complex structures of our bodies and brains would be reduced to streams of elementary particles. Yet the energy, the mass, and possibly the information that comprised us would persist in some form, eventually returning to the broader universe through the slow process of Hawking radiation. Whether this constitutes death or transformation depends partly on how we define these terms and how we understand the nature of identity and consciousness. From one perspective, it is clearly death, the end of our existence as coherent, conscious entities. From another, it might be seen as an extreme form of transformation, a dissolution of our current form and a dispersal of our components back into the cosmic whole. The black hole thus serves as a powerful metaphor for processes of ending and transformation, for the dissolution of form and the conservation of essence. It reminds us that even in the most extreme conditions imaginable, certain fundamental principles of physics continue to apply. Energy is conserved. Information, at least according to quantum mechanics, cannot be truly destroyed. Matter changes form but does not vanish from existence. As we approach the end of our theoretical journey into a black hole, we confront the limits not just of our physical survival, but of our scientific understanding. We approach domains where our current theories become incomplete or break down entirely, where the nature of reality at the most fundamental level remains uncertain. In this uncertainty lies both the challenge and the promise of future physics. The black hole stands as a cosmic question mark, a region where the mysteries are so profound that they may require not just incremental advances in our understanding, but revolutionary new insights into the nature of space, time, matter, and perhaps even consciousness itself. Death or transformation? The answer may be both, or neither, or something that transcends these categories entirely. The black hole reminds us that even our most fundamental concepts may need revision as we explore the extremes of physical reality, and that what appears to be an ending may, from a different perspective, be part of an ongoing cosmic process of change and renewal. A single second could contain the memory of all things before the end. What would it feel like to fall into a black hole? What would a conscious mind perceive as it approached and crossed the event horizon, as it experienced the extreme warping of space-time, as it journeyed toward the singularity? These questions take us beyond the mathematics of general relativity into the realm of subjective experience, where physics meets philosophy. For a human falling into a stellar mass black hole, the most immediately noticeable effect would be tidal forces. Even at a considerable distance from the black hole, the difference in gravitational pull between your head and your feet would become perceptible. As you approached, this difference would increase dramatically, creating a stretching sensation along the axis pointing toward the black hole and a compression perpendicular to this axis. For a black hole with a mass similar to our Sun, these tidal forces would become lethal long before you reached the event horizon. Your body would be stretched and compressed with such violence that no biological structure could withstand the strain. The technical term for this process, spaghettification, vividly captures the elongation that would occur. But for a supermassive black hole, with a mass millions or billions of times that of our Sun, the tidal forces at the event horizon could be quite mild. An astronaut crossing the horizon of such a black hole might not experience any unusual physical sensations at that moment. The fatal tidal forces would come later as they approached the central regions. So for our thought experiment, let us consider the conscious experience of falling into a supermassive black hole, where we might survive crossing the event horizon intact. What would we perceive, both visually and in terms of our broader experience? As we approach the black hole from a distance, the first notable visual effect would be gravitational lensing. The black hole itself emits no light, but we would see a dark circle against the background of stars. Light from stars behind the black hole would be bent around it, creating a distorted view of the cosmos. Stars near the apparent edge of the black hole would appear to stretch into arcs, forming partial or complete rings. This effect would become more pronounced as we drew closer. The visual distortion would extend to our view of all distant objects, as the curvature of space-time bent light in complex patterns. If the black hole is surrounded by an accretion disk, a swirling ring of superheated gas and dust, we would see this material glowing brightly, perhaps emitting X-rays and other high-energy radiation that would be invisible to our eyes but detectable with instruments. As we fell closer to the event horizon, the visual distortions would intensify. Looking outward, away from the black hole, we would see more and more of the universe compressed into a shrinking circular field of view. The entire cosmos that would normally surround us in all directions would be visible within this circle, with severe distortions near the edge. Looking toward the black hole, we would see only darkness, a perfect absence of light. This darkness would grow to fill more and more of our visual field as we approach the horizon. The boundary between the visible cosmos behind us and the darkness ahead would not be sharp, but would be mediated by the severely distorted images of objects whose light is being bent around the black hole. What about our perception of time? According to general relativity, time passes more slowly in stronger gravitational fields, an effect called gravitational time dilation. As we approach the black hole, time would flow more slowly for us compared to distant observers. But would we notice this change? From our own perspective, time would seem to pass normally. Our heart would beat at its usual rhythm. Our thoughts would flow at their usual pace. Our biological processes would continue as before. It is only by communicating with distant observers or by looking outward at the universe that we would become aware of the time dilation. If we could somehow maintain communication with observers far from the black hole, we would notice something remarkable. Messages from them would arrive at an accelerated pace from our perspective. It might seem as if the outside universe were experiencing a dramatic fast forward. Events that would take years or decades from the perspective of distant observers might unfold in minutes or seconds from our perspective. This effect would become more pronounced as we approach the event horizon. Near the horizon, we might witness what seems like eons of cosmic evolution in what feels to us like moments. Stars might be born, live out their lives, and die. Galaxies might evolve and transform. The universe itself might age dramatically from our perspective. What would we experience as we cross the event horizon itself? From a purely physical perspective, general relativity tells us that nothing special happens at the horizon itself. There is no physical barrier, no membrane, no wall that we would feel ourselves passing through. The laws of physics would continue to operate as they had before, and locally, space-time would still seem relatively flat and unremarkable. The key difference is that after crossing the horizon, all possible future paths lead toward the singularity. The direction outward, away from the black hole, simply ceases to exist as a possibility. But we would not immediately perceive this change in our fundamental situation. If we looked outward after crossing the horizon, we would still see the universe behind us, now compressed into an increasingly small circular field of view. Light from the outside universe can still reach us just after we've crossed the horizon, though it becomes increasingly redshifted and dimmed. Eventually, this window to the outside would close completely as all external light became too redshifted to detect. Inside the horizon, our subjective experience of time would continue, but something profound happens to the relationship between space and time. The radial coordinate, measuring the distance to the center of the black hole, takes on properties normally associated with time. Our movement toward the singularity becomes as inevitable as the forward flow of time itself. This shift in the nature of dimensions is difficult to translate into subjective experience. We might not perceive it directly, but we would notice its effects. No matter which direction we tried to move, no matter how much energy we expended, we would find ourselves drawn inexorably toward the center. It would be like trying to avoid moving from the present into the future, an inherently impossible task. As we continued our journey inward, the tidal forces would eventually become noticeable and then rapidly overwhelming. For a supermassive black hole, this might happen well after crossing the horizon, giving us time to observe our surroundings. But eventually, these forces would exceed what any biological structure could withstand. What would this feel like? Initially, it might be experienced as a gentle stretching sensation, a feeling of being pulled more strongly at our feet than at our head if we were falling feet first. This sensation would intensify, becoming uncomfortable and then painful as the forces exceeded what our bodies evolved to handle. Eventually, these forces would begin to damage our bodies at a cellular level. The connections between cells would be torn apart. Our organs would begin to fail. Our nervous system, including our brain, would start to lose its structural integrity. At this point, conscious experience, as we understand it, would likely cease. But before reaching this point, what might our conscious minds experience in the extreme environment of a black hole's interior? Here, we move from physics into more speculative territory, where the nature of consciousness itself becomes relevant. Some philosophers and neuroscientists propose that consciousness is generated by the integrated information processing in our brains. If this is the case, then as long as our brains maintain sufficient integrity to process information, some form of conscious experience might persist. But as the tidal forces began to disrupt this integration, our consciousness would likely fragment and ultimately dissolve. Others suggest that consciousness has aspects that transcend particular physical implementations, that it might be a more fundamental feature of the universe. From such perspectives, perhaps some form of consciousness could persist even as our physical brains were destroyed, though it would certainly not be consciousness as we normally experience it. Time perception in these final moments presents another fascinating question. In extreme situations, such as near-death experiences or traumatic events, people often report subjective time slowing down dramatically. A few seconds might feel like minutes or even hours as the brain processes information at an accelerated rate. In the extreme environment near a black hole's singularity, might something similar occur? Could our final moments of consciousness, as our physical structures begin to fail, contain a subjective eternity of experience? Could a single second, as measured by our rapidly failing biological clocks, contain what feels like an infinity of awareness? Some have speculated that the time dilation effects near a black hole, combined with the potential for altered states of consciousness in extreme conditions, might create an experience where subjective time stretches to extraordinary lengths. In the final approach to the singularity, as space-time itself approaches a point of infinite curvature, perhaps subjective experience might also approach a kind of infinity. This speculation resonates with ideas from various philosophical and mystical traditions, which sometimes describe states of consciousness where the ordinary experience of time is transcended, where a moment can contain eternity. The extreme physics of black holes might create conditions where such normally metaphorical notions take on a more literal meaning. Of course, all of this is highly speculative. We have no empirical data on consciousness in such extreme conditions, and our theories about the relationship between physical processes and subjective experience remain incomplete. But the questions themselves highlight the fascinating intersection of physics, neuroscience, and philosophy that black holes represent. What might we think about? What might occupy our awareness in these final moments? Perhaps we would reflect on our lives, on the journey that brought us to this extraordinary place. Perhaps we would contemplate the mysteries of the cosmos that we are now experiencing more directly than any human before us. Perhaps we would consider the nature of consciousness itself as ours approached its transformation or dissolution. Or perhaps, in the face of such overwhelming physical forces and the approach of the unknowable singularity, ordinary thought would give way to a more direct, immediate awareness, a pure experiencing of each moment as it unfolds. In the extremity of the situation, conceptual thinking might be replaced by a more primal form of consciousness. These reflections on the conscious experience of falling into a black hole remind us of how much remains unknown, not just about these cosmic objects, but about consciousness itself. They highlight the profound questions that arise at the intersection of our most advanced physical theories and our understanding of mind and awareness. In the end, the conscious experience of falling into a black hole would be a journey into the unknown, not just in terms of external reality, but in terms of the nature and limits of consciousness itself. It would be a journey toward conditions where our ordinary frameworks of understanding break down, where the familiar gives way to the unimaginable. As our theoretical journey continues, we carry these questions with us, recognizing that they represent not just scientific puzzles, but some of the most profound mysteries of existence. The black hole serves as both a physical reality and a powerful metaphor for the limits of our knowledge and experience, for the boundaries where the known gives way to the unknown and where transformation may await. Escape is not impossible to imagine, but perhaps not in any form we would recognize. Throughout our theoretical journey into a black hole, we have largely accepted the seeming inevitability of our fate. Once past the event horizon, all paths lead to the singularity. The laws of physics as we currently understand them offer no mechanism for escape. But what if we consider more speculative possibilities? Could sufficiently advanced technology offer any hope for survival or escape? Let us explore some theoretical scenarios that, while highly speculative, are not entirely ruled out by our understanding of physics. The first and most obvious approach would be to avoid crossing the event horizon in the first place. With sufficient propulsion technology, a spacecraft could maintain a stable orbit around a black hole, perhaps even a close orbit that allows for detailed study of the extreme gravitational effects near the horizon. Such orbits would require continuous thrust to counteract the gravitational pull, with the required energy increasing dramatically as the orbit approaches the photon sphere, the region where light itself can orbit the black hole. For a spacecraft that has not yet crossed the event horizon, escape is always theoretically possible, given sufficient energy. The challenge is generating enough thrust to overcome the intense gravitational pull. Even our most advanced current or near-future propulsion technologies would be inadequate for escaping from close proximity to a black hole. Chemical rockets, ion drives, nuclear thermal propulsion, even theoretical fusion drives would all fall far short of the required power. More exotic propulsion concepts might offer better possibilities. Antimatter engines, converting matter and antimatter directly into energy with perfect efficiency, could theoretically generate enough thrust to escape from relatively close to a black hole, though still not from the immediate vicinity of the event horizon. Even more speculative drives based on manipulating space-time itself, such as theoretical Alcubierre warp drives, might offer mechanisms to escape the black hole's influence, though such technologies remain firmly in the realm of science fiction rather than engineering possibility. But what if we have already crossed the event horizon? Here, conventional physics offers no path for escape. Once inside the horizon, all possible future trajectories lead to the singularity. No amount of thrust, no matter how powerful, can overcome this fundamental constraint of space-time geometry. To even imagine escape from behind the event horizon requires us to consider physics beyond our current understanding. One speculative approach involves quantum tunneling, a phenomenon where particles can occasionally pass through energy barriers that would be insurmountable according to classical physics. Quantum mechanics tells us that there is a non-zero probability for particles to tunnel through such barriers, effectively disappearing from one side and reappearing on the other. Could an object or information quantum tunnel out of a black hole? For macroscopic objects, the probability would be unimaginably small, effectively zero for any practical purpose. But for elementary particles or quantum bits of information, the possibility is not entirely ruled out. Stephen Hawking's work on black hole radiation suggests that quantum effects near the horizon can allow particles to escape that would be trapped according to classical general relativity. Taking this further, some speculative theories suggest that in a full quantum theory of gravity, which we do not yet possess, the event horizon might not be an absolute boundary. It might have quantum fuzziness or uncertainty that could, in principle, allow for some exchange of information between the interior and exterior. This idea connects to ongoing research on the black hole information paradox and the question of whether information that falls into a black hole is truly lost. Another exotic possibility involves the theoretical existence of white holes, which would be the time reversal of black holes. While a black hole allows matter and energy to flow in but not out, a white hole would allow them to flow out but not in. Some theoretical models suggest that black holes might transform into white holes after a certain point, potentially providing an exit for matter that fell in. However, this transformation, if it occurs at all, might take longer than the current age of the universe, making it of little practical use for escape. Even more speculative are theories suggesting connections between black holes and other universes. The Einstein-Rosen bridge, a non-traversable wormhole described by the Schwarzschild solution to Einstein's field equations, mathematically connects a black hole to a white hole, potentially in another universe or another region of our universe. While not traversable in its natural state, some theoretical physicists have explored whether such connections could, in principle, be modified to allow passage. Physicist Kip Thorne and his colleagues demonstrated that if exotic matter with negative energy density could be used to hold open the throat of a wormhole, it might become traversable. While we have no technology to create or manipulate such exotic matter, and it remains unclear whether it can exist in the quantities required, the physics does not completely rule out the possibility. Such a stabilized wormhole might, in principle, offer a path from the interior of a black hole to another location. Moving even further into speculative territory, some approaches to quantum gravity, particularly string theory and its offshoot M theory, suggest the possibility of extra dimensions beyond the three spatial dimensions we experience directly. In some models, our universe exists as a three-dimensional brane within a higher dimensional space. Black holes might connect to these extra dimensions, potentially offering escape routes not available in conventional four-dimensional spacetime. These ideas remain highly speculative and far beyond our current technological capabilities to explore or exploit. But they remind us that what seems like an absolute limitation within one physical theory might be transcended in a more comprehensive framework. Even if physical escape from inside the event horizon proves impossible, might there be other forms of survival or escape? Let us consider some even more speculative possibilities that touch on the nature of information and consciousness. If consciousness is fundamentally an information processing phenomenon, might it be possible to encode and transmit that information in forms that could escape a black hole? Hawking radiation, the quantum mechanical process by which black holes slowly lose mass and eventually evaporate, might offer a theoretical mechanism. Some theories suggest that this radiation carries information about what fell into the black hole, encoded in subtle quantum correlations. Could an advanced civilization find a way to encode consciousness or information in a form that could be carried out by this radiation? The technical challenges would be immense. Hawking radiation is incredibly faint for large black holes, and the encoding would need to overcome the extreme chaotic conditions inside the black hole. But the laws of physics do not entirely rule out such possibilities, at least in their most speculative interpretations. Another approach might involve the holographic principle, which suggests that all the information contained in a volume of space can be represented on the boundary of that region. Applied to black holes, this principle suggests that everything that falls in is somehow encoded on the event horizon itself. An advanced civilization might theoretically find a way to transfer consciousness or information to this boundary encoding, though again, the technical challenges would be beyond anything we can currently imagine. Even more speculative are ideas about the fundamental nature of consciousness itself. Some philosophical approaches, drawing on interpretations of quantum mechanics, suggest that consciousness might have aspects that transcend its particular physical implementation. If consciousness is not solely dependent on specific physical structures like brains, but has some more fundamental relationship to information, or even to the basic fabric of reality, then perhaps it might persist or transform rather than be destroyed in a black hole. These ideas take us far beyond established science into philosophical speculation, but they highlight an important point about technology and escape scenarios. Our conception of what constitutes escape or survival might need to expand beyond the physical preservation of bodies or objects. Information, patterns, or consciousness itself might be what persists or escapes, rather than any material structure. For a civilization sufficiently advanced beyond our own, the distinction between material existence and information might blur or transform. Such a civilization might view entry into a black hole not as destruction, but as transition to another form or state, a transformation rather than an ending. All of these speculative scenarios remain firmly in the realm of imagination rather than practical possibility for our current technology. Even the most advanced technologies we can realistically envision for the coming centuries would fall far short of what would be required to implement any of these escape strategies. Yet there is value in considering these possibilities not just as interesting thought experiments, but as explorations of the fundamental nature of reality and the ultimate limits of technology. The boundaries of what is physically possible are defined not just by our current understanding, but by the actual laws of nature, which we continue to explore and refine. The history of science and technology is filled with examples of what once seemed impossible becoming commonplace. Heavier than air flight, instantaneous global communication, manipulation of matter at the atomic level, all would have seemed like impossible magic to earlier generations. While this does not mean that all imagined technologies will eventually become possible, it does suggest caution in declaring absolute limits to future capability. When considering black holes and potential escape scenarios, we are operating at the very frontier of our understanding of physics. General relativity and quantum mechanics, our two most successful physical theories, have not yet been fully reconciled. Both are surely incomplete descriptions of reality, approximations that work extraordinarily well in their domains, but that must give way to a more comprehensive theory in extreme conditions like those inside a black hole. What might such a more comprehensive theory allow? Would it open possibilities for escape or survival that are unimaginable within our current frameworks? We cannot know, but the history of science suggests that the universe often proves more surprising and more rich with possibility than our limited imaginations can anticipate. For now, the most plausible approach to black hole survival remains avoiding entry in the first place. With sufficient advanced warning and propulsion technology, a spacecraft approaching a black hole could execute a slingshot maneuver, using the black hole's gravity to accelerate and change direction before crossing the point of no return. Such maneuvers are routinely used by current space missions to gain velocity from planetary flybys, though executing them near a black hole would require far more precise calculations and more powerful propulsion. For a civilization capable of interstellar travel, black holes might actually become valuable resources rather than merely hazards to be avoided. The intense gravitational field of a black hole could be used for gravitational assist maneuvers, potentially accelerating spacecraft to velocities difficult to achieve by other means. The energy in the accretion disk surrounding many black holes represents a potentially vast resource, if it could be safely harvested. Some speculative propulsion concepts even suggest using the Hawking radiation from small, artificially created black holes as a drive mechanism. Such concepts remain far beyond our current capabilities, but illustrate how these extreme objects might eventually be seen as tools rather than merely as cosmic destructive forces. As we contemplate these technological possibilities and escape scenarios, we are reminded of the intimate connection between understanding and capability. Each advance in our comprehension of black hole physics opens new possibilities, not just for theorizing about escape, but for imagining how these extraordinary objects might relate to the future of intelligent life in the cosmos. If the universe as we currently understand it continues to expand at an accelerating rate, galaxies will eventually become isolated from one another, with the space between them expanding faster than light can travel across it. In such a universe, black holes and their properties might become essential for the long-term survival of advanced civilizations, perhaps offering the only remaining connections across an otherwise uncrossable cosmic void. The Penrose process, a theoretical mechanism for extracting energy from a rotating black hole, might provide power long after stars have burned out. The time dilation effects near black holes might offer a way to survive across cosmic timescales that would otherwise be unimaginably vast. And if any of the more exotic possibilities we have considered, such as connections to other universes or dimensions, prove to have any basis in reality, black holes might ultimately represent doorways rather than dead ends. All of this remains highly speculative, firmly in the domain of theoretical physics and science fiction rather than practical technology. Yet such speculation serves a purpose beyond mere entertainment. It pushes us to clarify the boundaries of what we know and what we merely assume, to distinguish between fundamental limitations imposed by the laws of physics and practical challenges that might, in principle, be overcome. For our theoretical journey into a black hole, these speculations about technology and escape scenarios offer a counterpoint to the seemingly inevitable progression toward destruction at the singularity. They remind us that even in the most extreme environments, possibility may exist alongside constraint, that transformation might accompany destruction, and that what appears to be an ending from one perspective might, from another, be part of a larger process or transition. Escape from a black hole may indeed be impossible in the form we would immediately recognize as physical objects moving back across the event horizon into the universe we know. But escape or survival in other forms, as information, as patterns, as transformed entities, remains at least conceivable within some speculative frameworks. As we continue our journey, deeper into the black hole and closer to its central mysteries, we carry with us not just an acceptance of apparent physical limitations, but also an openness to transformative possibilities, an awareness that the universe has often proved stranger and more wonderful than our limited imaginations can anticipate. You may fall inward, but your imprint remains. Among the most profound and counterintuitive ideas to emerge from the study of black holes is the holographic principle, a revolutionary concept that suggests reality may be fundamentally different from our everyday perception of it. This principle proposes that all the information contained within a volume of space can be represented on the boundary of that region, much like a two-dimensional hologram can create the illusion of a three-dimensional image. The origins of the holographic principle can be traced to black hole thermodynamics, an area of research pioneered by Jacob Bekenstein and Stephen Hawking in the 1970s. Their work revealed a surprising connection between the laws of thermodynamics, which govern heat and energy, and the properties of black holes, which had previously been considered purely gravitational objects. Bekenstein discovered that black holes possess entropy, a thermodynamic property that measures disorder or information content. More specifically, he found that this entropy is proportional to the surface area of the black hole's event horizon, not to its volume, as one might intuitively expect. This was the first hint that information in a black hole might be encoded on its boundary rather than distributed throughout its interior. Hawking's subsequent discovery that black holes emit radiation, now known as Hawking radiation, further strengthened this connection to thermodynamics. This radiation gives black holes a temperature, completing their description as thermodynamic objects. The temperature is inversely proportional to the black hole's mass, meaning that smaller black holes are hotter and evaporate more quickly. These discoveries laid the groundwork for what Dutch physicist Gerard 't Hooft and American physicist Leonard Susskind would later formalize as the holographic principle. The principle emerged partly as a potential resolution to the black hole information paradox, the puzzle about whether information that falls into a black hole is truly lost or somehow preserved. The holographic principle suggests that when an object falls into a black hole, while the physical object indeed passes through the event horizon and continues toward the singularity. The information describing that object becomes encoded on the horizon itself. In a sense, the event horizon acts as a kind of cosmic memory surface, recording and storing information about everything that has fallen in. This idea challenges our intuitive understanding of how information and physical reality relate to each other. We typically think of information as being contained within physical objects, with complex three-dimensional structures holding correspondingly complex information. The holographic principle inverts this relationship, suggesting that the information came first and that our three-dimensional reality emerges from it. To understand how this might work, consider an analogy with actual holograms. A conventional hologram is a two-dimensional surface that, when illuminated correctly, creates the appearance of a three-dimensional object. The information needed to recreate the three-dimensional image is encoded in the interference patterns on the two-dimensional holographic film. Similarly, the holographic principle suggests that our three-dimensional reality might be encoded in patterns on a two-dimensional surface. Applied to black holes, this principle suggests that everything that falls in is simultaneously inside the black hole, progressing toward the singularity and encoded on the event horizon. These are not two separate copies, but two different ways of describing the same physical reality, like two different languages expressing the same meaning. This duality between a bulk description, dealing with the volume of space, and a boundary description, focusing on the surface enclosing that volume, has found its most precise mathematical expression in the ADES-CFT correspondence, discovered by Argentine physicist Juan Maldacena in 1997. This correspondence, developed within string theory, established an exact equivalence between a gravitational theory in a space with negative curvature, anti-de Sitter space, and a quantum field theory without gravity defined on the boundary of that space. While the ADES-CFT correspondence applies to a specific theoretical setup, rather than to our actual universe, it provides a concrete mathematical example of how the holographic principle might work. It has become one of the most studied areas in theoretical physics, offering insights not just into black holes, but into quantum gravity, strongly coupled quantum systems, and the fundamental nature of space-time itself. For our theoretical journey into a black hole, the holographic principle offers a fascinating perspective. As we cross the event horizon and descend toward the singularity, our physical forms indeed continue inward, subjected to the ever-increasing tidal forces until eventual destruction. But simultaneously, from another perspective, the information that constitutes us becomes encoded on the event horizon, preserved in the complex quantum state of the horizon itself. This dual description raises profound questions about identity and consciousness. If the information that defines us exists in two different representations, one inside the black hole and one on its boundary, which is the real us? Both descriptions are physically equivalent according to the holographic principle, yet they seem to imply very different fates. From the perspective of an outside observer, who never sees anything actually cross the event horizon due to the infinite time dilation at the horizon, we never completely enter the black hole. Instead, our information gets smeared across the horizon, eventually to be released back to the universe through the slow process of Hawking radiation over unimaginably long timescales. From our own perspective as we fall in, we cross the horizon in a finite and typically brief time, continuing toward the singularity, apparently disconnected from any boundary encoding. Yet the holographic principle insists that these two perspectives, however different they seem, are actually complementary descriptions of the same physical reality. This complementarity principle, proposed by Susskind, 't Hooft, and others, suggests that while these two descriptions may seem contradictory, they never lead to actual contradictions, because no single observer can access both perspectives simultaneously. An outside observer never sees anything cross the horizon, while an infalling observer, once inside, cannot communicate with the outside world. For consciousness, this raises intriguing possibilities. If consciousness is fundamentally an information processing phenomenon, and if that information is preserved in the holographic encoding on the event horizon, might some form of consciousness persist there, even as our physical forms are destroyed inside? Might there be a sense in which we continue to exist in a transformed state on the boundary, even as we cease to exist in our familiar form in the interior? These questions take us far beyond established science into philosophical speculation, but they highlight how the holographic principle challenges not just our understanding of black holes, but our conception of reality itself, suggesting that the physical world we perceive might be a kind of projection or emergence from a more fundamental description in terms of information on a boundary. The holographic principle also has implications for the black hole information paradox. If information is preserved on the horizon, and if that information is eventually released through Hawking radiation as the black hole evaporates, then information is not truly lost. It is transformed and redistributed, perhaps in ways that make it practically impossible to reconstruct the original configuration, but not fundamentally destroyed. This view is supported by theoretical work suggesting that Hawking radiation is not completely thermal or random, but contains subtle correlations that encode information about what fell into the black hole. These correlations might be extraordinarily complex and practically impossible to decode, but they would preserve the underlying quantum information in principle. Some researchers have proposed that the apparent loss of information in a black hole might be similar to the apparent irreversibility we see in thermodynamics. When an ice cube melts in a glass of water, the molecules of the ice cube spread throughout the glass. Reversing this process, spontaneously reforming the ice cube from the slightly warmer water, is not impossible according to the fundamental laws of physics, but is so improbable as to be effectively ruled out. Similarly, the information that falls into a black hole might be scattered in an effectively irreversible way, though not truly destroyed. The holographic principle extends beyond black holes to cosmology. Some theories suggest that our entire universe might be holographic, with all the information within our cosmic horizon encoded on that horizon. This would mean that the three-dimensional space we experience, with its galaxies, stars, planets, and living beings, might be emergent from a more fundamental description in terms of information on a distant cosmic boundary. This idea finds support in certain approaches to quantum gravity, which suggests that space-time itself is not fundamental, but emerges from more basic quantum mechanical processes. If true, this would represent one of the most profound shifts in our understanding of reality, since Einstein showed that space and time themselves are not fixed and absolute, but dynamic and relational. For our theoretical journey, the holographic principle offers a kind of cosmic reassurance. Even as we approach apparent destruction at the singularity, some aspect of us, the information that defines us, remains preserved on the boundary. We are not completely lost to the universe, but transformed and encoded in a different form. This encoding is not a separate copy or a backup, but an alternative description of the same physical reality. According to the holographic principle, the boundary description is not subordinate to the bulk description, but equivalent to it, two different languages expressing the same underlying truth. The mathematical foundations of the holographic principle are complex and still being developed. The ADS-CFT correspondence provides the most concrete example, but extending these ideas to our actual universe, which is not anti-de Sitter space, but appears to have a positive cosmological constant, remains an active area of research. Similarly, applying these principles to realistic black holes, rather than the idealized theoretical models where the mathematics is most clearly developed, introduces additional complexities. Yet despite these ongoing challenges, the holographic principle has become a cornerstone of modern theoretical physics, influencing research not just in black hole physics, but in quantum gravity, string theory, condensed matter physics, and quantum information science. It represents one of the most significant conceptual advances to emerge from the study of black holes, transforming our understanding not just of these extreme cosmic objects, but of the nature of space, time, and information themselves. As we contemplate these ideas, we are reminded of how profoundly black holes have transformed our understanding of physics. What began as curious mathematical solutions to Einstein's equations have become portals to new ways of thinking about reality itself. Black holes are not just the most extreme objects in the universe, but windows into the deepest aspects of physical law. The holographic principle, in particular, illustrates how the study of these cosmic objects can lead to insights that transcend astronomy and touch on the fundamental nature of reality. By pushing our theories to their limits, black holes have forced us to reconsider basic assumptions about how the universe works. For anyone contemplating a journey into a black hole, the holographic principle offers both comfort and complexity. It suggests that even as we approach apparent destruction, something of us persists, encoded in the quantum state of the horizon itself. Yet it also challenges our intuitive understanding of identity and existence, suggesting that we might simultaneously exist in multiple equivalent descriptions, each with its own apparent fate. In the mirror of the event horizon, we see not just our own reflection, but a deeper reflection of reality itself, a hint that the universe may be structured in ways far more subtle and complex than our everyday experience suggests. The boundary becomes as important as the interior, the surface as fundamental as the volume, and information as basic as matter and energy. As we continue our theoretical journey deeper into the black hole, we carry with us this dual perspective, aware that even as we progress toward the singularity, our imprint on the horizon remains, a holographic encoding that preserves at least the information content of our existence. We are simultaneously falling inward and remaining encoded on the boundary, a paradoxical state that reflects the strange cosmic logic of these most extreme objects in the universe. And so we approach the central mystery, the singularity itself, carrying not just questions about our own fate, but about the nature of reality, the relationship between information and physical existence, and the possibility that what seems like an ending might, from another perspective, be part of a larger process of cosmic information processing and transformation. At the center, there may be nothing, or everything, a question that no one can answer. As our theoretical journey through a black hole approaches its culmination, we confront the ultimate mystery, the singularity at the center. According to classical general relativity, this is a point, or in the case of rotating black holes, a ring, where matter is compressed to infinite density, space-time is infinitely curved, and the known laws of physics break down entirely. Yet this mathematical description may not represent physical reality. The prediction of a true singularity is generally regarded as a sign that the theory has been pushed beyond its domain of validity, that a more comprehensive theory is needed to describe what actually happens at the center of a black hole, what might lie at the heart of a black hole. Let us explore the possibilities, from the most conventional predictions of current physics to the most speculative ideas at the frontiers of theoretical research. The simplest type of black hole described by general relativity is the Schwarzschild black hole, named after Karl Schwarzschild, who discovered this solution to Einstein's field equations in 1916. This model describes a non-rotating, electrically neutral black hole, where all the mass is concentrated at a central point of infinite density, the singularity. Surrounding this singularity is the event horizon, a spherical boundary from which nothing, not even light, can escape. For a Schwarzschild black hole, the singularity is a point in both space and time. It represents not just a location, but a moment, a future that all infalling matter inevitably encounters. The mathematics of general relativity predicts that as matter approaches this singularity, tidal forces become infinite, stretching and compressing any object with unlimited strength. Space-time curvature likewise becomes infinite, and all known physical laws cease to provide meaningful predictions. But most black holes in the universe are not expected to be of the simple Schwarzschild type. They are likely to be rotating, described instead by the Kerr solution to Einstein's equations, discovered by New Zealand mathematician Roy Kerr in 1963. For these rotating black holes, the central singularity takes the form not of a point, but of a ring in the equatorial plane of the black hole's rotation. This ring singularity has some remarkable mathematical properties. Unlike the point singularity of a Schwarzschild black hole, which all infalling matter must eventually encounter, the ring singularity of a Kerr black hole could theoretically be avoided. An object falling into a rotating black hole along the axis of rotation might pass through the ring without hitting the singularity itself. The mathematics further suggests that passing through the ring could lead to another region of space-time, sometimes called a white hole or even another universe. In the maximally extended Kerr solution, The ring singularity connects to another asymptotically flat region, potentially offering a passage to elsewhere. However, most physicists believe that in realistic black holes, this passage would be unstable and effectively blocked by various physical effects, not captured in the idealized mathematical model. Both the point and ring singularities predicted by general relativity are often called singularities. This means that at these locations, physical quantities such as density and spacetime curvature become infinite. In physics, the prediction of a true infinity is typically interpreted not as a feature of reality, but as a sign that the theory being used has reached its limits of applicability. General relativity is a classical theory, meaning it does not incorporate quantum effects, which must become important in regions of extreme density and curvature. Most physicists expect that a full theory of quantum gravity would eliminate the singularity, replacing it with something physically meaningful, though exactly what remains a subject of intense theoretical research. One approach to resolving the singularity comes from loop quantum gravity, a theory that suggests spacetime itself has a discrete granular structure at the smallest scales, rather like the pixels in a digital image. In this framework, there is a minimum possible size to regions of space, preventing the infinite compression that would create a true singularity. Instead, matter would be compressed to an extremely high but finite density, and spacetime curvature would likewise reach a maximum finite value. Some models within loop quantum gravity suggest that the center of a black hole might contain a region of highly compressed matter, a kind of exotic state unlike anything we encounter in normal circumstances, but still described by physical laws. This region might even undergo a bounce, expanding again in a way that connects to another region of spacetime, effectively turning the black hole into a bridge or tunnel. String theory, another approach to quantum gravity, offers different perspectives on what might replace the singularity. In string theory, the fundamental constituents of reality are not point particles, but tiny, one-dimensional strings. These strings can vibrate in different ways, giving rise to the various particles and forces we observe. Because strings have extension, they cannot be compressed to a true point, potentially avoiding the infinite densities predicted by general relativity. Some string theory models suggest that the interior of a black hole might contain a fuzzball, a complex, horizon-sized quantum object with no interior or singularity in the conventional sense. In this view, the information about whatever falls into a black hole is stored in subtle quantum modifications to the horizon itself, and the interior, as described by classical general relativity, is an approximation that breaks down completely near what would be the singularity. Another possibility is that the center of a black hole might contain what physicist Carlo Rovelli and others have called a Planck star. This would be an object with a size on the order of the Planck length, about 10 to the power of -35 meters, the scale at which quantum gravity effects are expected to become dominant. A Planck star would be incredibly dense, but not infinitely so, and might exhibit exotic quantum properties that prevent further collapse. Some even more speculative ideas suggest connections between black holes and the creation of new universes. Cosmologist Lee Smolin has proposed a theory of cosmological natural selection, where black holes might give birth to new universes with slightly different physical constants. In this scenario, the singularity would be a kind of quantum transition point where a new expanding universe emerges, causally disconnected from our own, but inheriting certain characteristics from the black hole that created it. The concept of naked singularities adds another layer of complexity to our exploration. In general relativity, the cosmic censorship hypothesis, proposed by Roger Penrose, suggests that all physically realistic singularities should be hidden behind event horizons, preventing them from being observed from the outside universe. A naked singularity, one not shrouded by an event horizon, would be visible to distant observers and could potentially lead to causality violations and other physically problematic situations. While most solutions to Einstein's equations that contain naked singularities are considered unphysical or require special, finely tuned conditions, their potential existence cannot be entirely ruled out. If they do exist, they would represent locations where the breakdown of known physics would be observable from the outside, rather than being hidden behind the cosmic censorship of an event horizon. Another intriguing possibility involves the concept of firewalls, proposed as a potential resolution to tensions between general relativity and quantum mechanics near the event horizon. In this scenario, the area just inside the horizon would become a region of highly energetic particles, effectively creating a wall of fire that would destroy anything crossing the horizon. This would prevent the formation of a conventional singularity by consuming infalling matter before it could reach the center. The firewall hypothesis remains controversial, with many physicists arguing that a less violent resolution to the tensions between quantum mechanics and general relativity must exist. But it illustrates the profound challenges in reconciling our current theories at the extreme conditions inside a black hole. All of these possibilities remain speculative, existing at the frontiers of theoretical physics, where our most successful theories begin to strain or conflict with each other. What is clear is that the classical prediction of a true singularity is almost certainly incorrect, a sign that new physics must enter at these extreme scales. For our theoretical journey, approaching the center of a black hole means entering a domain where established science gives way to speculation, where the mathematics of general relativity predicts its own failure, and where various candidate theories of quantum gravity offer different visions of what might replace the singularity. If we were somehow able to survive the journey to the central regions of a black hole, what might we experience as we approached what classical general relativity calls the singularity? The answer depends entirely on which of the speculative theories proves correct, or whether the actual physics introduces possibilities we have not yet imagined. If loop quantum gravity or similar theories are on the right track, we might encounter a region of extremely curved spacetime, compressed to the minimum possible scale allowed by quantum effects. Instead of experiencing infinite tidal forces, we might find them reaching a maximum intensity that, while far beyond what any physical structure could withstand, stops short of the true infinity predicted by classical theory. If certain string theory models are correct, we might discover that the apparent singularity dissolves into a complex quantum state as we approach, with the classical description of spacetime giving way to something more fundamental, perhaps the vibrations of strings in higher dimensions or some other structure currently beyond our ability to visualize clearly. If models involving a bounce or transition to another region of spacetime are correct, we might, after experiencing extreme but finite conditions, find ourselves emerging into a different domain, perhaps another universe with its own physical laws, or a different region of our own universe. This would represent not an ending, but a passage, a transformation from one state to another. The diversity of these possibilities highlights how little we truly know about the central mysteries of black holes. We have developed sophisticated mathematical models and theoretical frameworks, but direct observational evidence remains limited, and the extreme conditions at the center of a black hole remain beyond our current ability to probe experimentally. Even our most advanced astronomical observations, such as the Event Horizon Telescope's imaging of the shadow of the supermassive black hole at the center of galaxy Messier 87, can only observe the region near the event horizon, not the interior. The detection of gravitational waves from merging black holes likewise provides information about their masses, spins, and the dynamics of the merger, but not about the nature of their interiors. The center of a black hole thus remains one of the greatest mysteries in physics, a domain where our theories predict their own failure and where new, more comprehensive frameworks are needed. It stands as a humbling reminder of the limits of our current understanding and of the vast territory still to be explored at the frontiers of fundamental physics. For philosophers and those interested in the broader implications of these cosmic mysteries, black hole singularities raise profound questions about the nature of physical law, the limits of scientific knowledge, and the relationship between mathematics and physical reality. If singularities represent breakdowns in our theories rather than features of reality, what does this tell us about the status of physical laws? Are they universal and absolute, or are they approximations that apply within certain domains but break down at extremes? The various proposed resolutions to the singularity problem also connect to deeper philosophical issues about the nature of space, time, and causality. If the center of a black hole contains a transition to another universe or region of space-time, what does this imply about the structure of reality as a whole? Is our universe part of a larger multiverse, connected through the centers of black holes? Do the laws of physics themselves evolve through such connections, as in Smolin's cosmological natural selection? The question of naked singularities connects to issues of determinism and predictability in physics. If naked singularities can exist, regions where physics as we understand it breaks down would be visible to the outside universe, potentially allowing for causal influences or events not predictable from initial conditions. This would challenge the deterministic framework that underlies much of classical physics. The problem of information preservation in black holes likewise raises deep questions about the fundamental nature of reality. Is information truly fundamental, as suggested by certain interpretations of quantum mechanics and the holographic principle? Or is it an emergent property, dependent on the physical structures that embody it? The fate of information in black holes might help clarify these foundational issues. For our theoretical journey, approaching the center of a black hole means confronting not just the limits of our physical theories, but the boundaries of knowledge itself. We enter a domain where certainty gives way to possibility, where established frameworks fail, and where the unknown predominates over the known. Yet this uncertainty is not a failure of science but a frontier, an opportunity for new discoveries and deeper understanding. The history of physics is filled with examples where apparent breakdowns in existing theories led to revolutionary new frameworks, from the ultraviolet catastrophe in black body radiation that helped give birth to quantum mechanics, to the apparent paradoxes of simultaneity that Einstein resolved with special relativity. The center of a black hole may prove to be a similar catalyst for theoretical advance, a cosmic puzzle that drives us toward a more comprehensive understanding of the fundamental nature of reality. The various approaches being explored today, from loop quantum gravity to string theory, from firewalls to fuzzballs, represent attempts to peek beyond the limits of our current theories, to glimpse what might lie at the heart of these most extreme objects in the universe. As we contemplate these possibilities, we are reminded of the remarkable journey of discovery that has brought us to our current understanding of black holes. From purely mathematical solutions to Einstein's equations, regarded initially as mere curiosities, they have become central to our understanding of astrophysics, fundamental physics, and even the nature of information and reality itself. The center of a black hole represents perhaps the ultimate mystery in this journey, a point where our theories predict their own inadequacy and where new physics must enter. It stands as both a challenge and an opportunity, a cosmic question mark that may eventually lead to answers about the deepest aspects of physical reality. For now, we must acknowledge the limits of our knowledge and the speculative nature of all attempts to describe what lies at the center of a black hole. We cannot say with certainty whether it contains nothing or everything, a point of infinite density or a transition to elsewhere, a true end or a new beginning. We can only explore the possibilities allowed by our best theoretical frameworks and await the development of more comprehensive theories that might someday provide more definitive answers. As our theoretical journey approaches this central mystery, we prepare to confront not just the unknown, but the potentially unknowable, regions where the framework of scientific knowledge itself may reach its limits. Yet we proceed with the curiosity and wonder that have driven scientific exploration from its beginnings, ready to be surprised, confounded, and enlightened by whatever we might discover. Perhaps someday, theoretical advances in quantum gravity or related fields will provide a clearer picture of what lies at the center of a black hole. Perhaps new observational techniques will offer indirect glimpses of the physics at these extreme scales. Or perhaps the center of a black hole will remain an enduring mystery, a cosmic koan that resists final resolution but continues to inspire new questions and new approaches to understanding the fundamental nature of reality. For now, we can say only that at the center of a black hole lies one of the greatest puzzles in physics, a domain where established theories break down and where the nature of space, time, matter, and information may be transformed in ways we are only beginning to imagine. It is a fitting culmination to our journey, a reminder that exploration does not always lead to definitive answers, but sometimes to deeper and more profound questions. As we approach the end of our theoretical exploration, we recognize that the mystery at the center of a black hole is not just a scientific puzzle, but a metaphor for the human quest for understanding itself. Just as we have ventured in imagination toward the most extreme environment known to physics, so humanity continues to press against the boundaries of the known, driven by curiosity and wonder to explore the deepest mysteries of existence. The center of a black hole reminds us that this quest has no final endpoint, no physical objects, but as profound tests of the limits of our knowledge, as mirrors reflecting the strengths and limitations of the scientific enterprise itself. In this chapter, we explore what science can and cannot know about black holes, and what these cosmic enigmas reveal about the nature of scientific knowledge more broadly. The scientific study of black holes represents one of humanity's greatest intellectual achievements. From purely mathematical solutions to Einstein's field equations, regarded initially as mere curiosities, black holes have become central to our understanding of astrophysics, fundamental physics, and even information theory. This journey has demonstrated the remarkable power of theoretical physics to explore domains far beyond our direct experience, using mathematics and logical inference to probe the most extreme environments in the universe. Yet this same journey has revealed inherent limitations in our ability to know certain aspects of black holes with certainty. These limitations arise from multiple sources, some practical, some theoretical, and some potentially fundamental to the nature of knowledge itself. The most obvious limitation is observational. The defining feature of a black hole, its event horizon, marks a boundary beyond which no information can reach outside observers. The interior of a black hole is, by definition, invisible to us. No light, no radiation, no signals of any kind can emerge from behind the horizon to be detected by our instruments. This creates an absolute observational limit, a cosmic curtain behind which our telescopes and detectors cannot peer. This does not mean we cannot study black holes scientifically. We can observe their effects on surrounding matter and space-time. We can detect the gravitational waves produced when black holes merge. We can image the hot gas swirling around them, as the Event Horizon Telescope did for the supermassive black hole at the center of galaxy Messier 87. We can measure their masses and spins through their gravitational influences, but we cannot directly observe their interiors. Some have suggested that this observational limit makes the interiors of black holes unscientific, mere speculation rather than proper subjects for scientific study. But this view misunderstands the nature of scientific inference. Science has always dealt with domains that cannot be directly observed, from the interior of atoms to the cores of stars, from the distant past to the far future. In each case, scientists use theories validated in observable domains to make inferences about the unobservable, constructing models that can be tested indirectly through their observable consequences. Black hole interiors represent an extreme case of this inferential approach. While we cannot directly observe them, we can develop theoretical models based on our best physical theories and test these models through observations of black hole exteriors and other phenomena where the same physical principles apply. These models may remain more uncertain than those in directly observable domains, but they are not mere speculation. They are grounded in established physical principles and constrained by observational data. Yet there is a deeper limitation that affects our knowledge of black hole interiors, one that goes beyond the practical challenge of observation. This is the theoretical breakdown that occurs at the singularity. According to general relativity, at the center of a black hole lies a point, or in the case of rotating black holes, a ring, where space-time curvature and matter density become infinite. At such a singularity, the equations of general relativity cease to provide meaningful predictions. The theory effectively predicts its own failure. This breakdown is not unique to general relativity. All of our current physical theories have domains of applicability beyond which they cease to be reliable. Newtonian mechanics breaks down at speeds approaching that of light or in very strong gravitational fields. Quantum mechanics, as currently formulated, has difficulty with strongly coupled systems and with incorporating gravity. Even our most comprehensive frameworks, like quantum field theory, have regimes where their calculations yield infinities or become intractable. The singularity at the center of a black hole represents perhaps the most dramatic example of such a theoretical boundary. It is a point where our current best theory of gravity, general relativity, predicts conditions that the theory itself cannot describe. This self-limiting quality is often interpreted not as a failure of science, but as a signpost pointing toward the need for a more comprehensive theory, one that can describe the physics of extreme gravitational fields where quantum effects become important. The quest for such a theory of quantum gravity represents one of the greatest challenges in contemporary theoretical physics. Approaches like string theory, loop quantum gravity, causal set theory, and others offer potential frameworks for understanding what happens at and near the singularity. But these theories remain incomplete and largely untested, operating at the speculative frontier of physics rather than within its established core. This situation creates a domain of scientific uncertainty that is deeper than mere lack of observational data. Even with perfect theoretical knowledge of the initial conditions outside a black hole, and even with a complete understanding of the laws of physics as they operate in accessible regimes, we cannot with current theories predict with certainty what happens at the singularity. There is a fundamental gap in our theoretical framework. Some philosophers of science have suggested that this gap might represent not just a current limitation, but a genuine boundary to scientific knowledge. Perhaps there are aspects of reality that are in principle unknowable, domains where the very concepts of natural law and predictability break down. The singularity might be such a domain, a point where nature itself becomes in some sense indescribable within any mathematical framework humans could comprehend. Others view this more optimistically as a temporary limitation that will be overcome with the development of a complete theory of quantum gravity. In this view, the apparent breakdown at the singularity is not a fundamental limit to knowledge, but a sign that our current theories are incomplete approximations to a more comprehensive framework that would remove the singularity entirely. The black hole information paradox, which we explored earlier, represents another frontier of scientific knowledge. The question of whether information that falls into a black hole is truly lost or somehow preserved and returned to the universe through Hawking radiation touches on fundamental principles of quantum mechanics and thermodynamics. The various proposed resolutions to this paradox, from information encoding in subtle correlations to the holographic principle, represent not just technical solutions to a specific problem, but profound reconsiderations of the nature of information, space, time, and causality. Even Hawking radiation itself, though widely accepted theoretically, has yet to be observed directly. The radiation from astrophysical black holes would be extremely faint and completely swamped by other cosmic radiation sources. Microscopic black holes, which might produce detectable Hawking radiation, have not been found naturally and have not been created in particle accelerators, despite some speculative concerns prior to the operation of the Large Hadron Collider. This creates another domain where theory has outrun observation, where our understanding remains theoretical rather than empirically confirmed. Yet it would be a mistake to conclude that our knowledge of black holes is fundamentally uncertain or unscientific. Much of what we understand about these objects is on very solid theoretical and observational ground. The basic features of black holes, their formation from collapsed stars or other concentrated matter, their gravitational effects on surrounding objects, the structure of space-time outside the event horizon. All these aspects are well established and repeatedly confirmed by astronomical observations. Even some aspects of black hole interiors, particularly the regions just inside the event horizon where space-time curvature remains relatively mild, can be described with confidence based on general relativity. It is primarily as we approach the singularity that our knowledge becomes increasingly uncertain and speculative. This gradient of certainty, from the well-established to the highly speculative, is characteristic not just of black hole physics, but of science more broadly. In any field, there is a spectrum from the firmly established core to the speculative frontier. What makes black holes particularly fascinating is the sharpness of the transition, the way they take us from the realm of precise prediction to the domain of theoretical breakdown over a relatively short conceptual distance. The study of black holes also highlights the role of mathematics in scientific understanding. Much of what we know about these objects comes not from direct observation, but from mathematical analysis of Einstein's field equations and related theoretical frameworks. This illustrates both the power and the limitations of the mathematical approach to nature. Mathematics allows us to explore domains beyond direct experience, to make precise predictions about phenomena we cannot observe directly, and to discover connections between apparently disparate aspects of reality. Yet mathematical models are always idealizations, simplified representations that capture some aspects of reality while necessarily omitting others. When these models predict their own breakdown, as general relativity does at the singularity, we confront the limits of this mathematical approach. Some philosophers and physicists have suggested that a complete understanding of black holes, particularly their interiors, might require not just new theories, but new ways of thinking about scientific knowledge itself. Perhaps the classical ideal of complete predictability, of being able to calculate with precision the outcome of any physical situation given sufficient initial information, simply does not apply in these extreme domains. Perhaps we need a more probabilistic, less deterministic conception of natural law, one that acknowledges inherent limits to prediction and control. Others have proposed that black holes might be fully understood only through a more holistic approach, one that considers the entire system, including the observer, rather than treating the black hole as an isolated object to be studied from the outside. The complementarity principle proposed by Leonard Susskind, which suggests that the interior and exterior views of a black hole are different but equally valid descriptions of the same physical reality, points in this direction. The various approaches to quantum gravity being developed today represent not just new theories, but often new frameworks for thinking about space, time, and physical law. String theory suggests that the fundamental constituents of reality are not point particles, but extended objects, one-dimensional strings whose vibrations give rise to the particles and forces we observe. Loop quantum gravity proposes that space-time itself has a discrete quantum structure at the smallest scales. These and other approaches challenge our conventional understanding of the nature of physical reality. What science can know about black holes, then, depends not just on observational capabilities or mathematical techniques, but on the adequacy of our conceptual frameworks, our ways of thinking about and representing the physical world. The study of black holes pushes these frameworks to their limits and beyond, forcing us to reconsider basic assumptions and develop new conceptual tools. This process of conceptual evolution is characteristic of major advances in science. Newton's laws gave way to Einstein's relativity, not just through new mathematics, but through a fundamental reconception of space, time, and gravity. Quantum mechanics emerged not just from new experimental data, but from a radical rethinking of the nature of matter, energy, and measurement. The full understanding of black holes may require a similar conceptual revolution. For now, what science cannot know about black holes with certainty includes the exact nature of the singularity, the ultimate fate of information that falls into a black hole, and the precise description of the physics in regimes where both strong gravity and quantum effects are important. These unknowns are not failures of science but frontiers, areas where current theories reach their limits and where new approaches are being developed. What science can know includes the formation and evolution of black holes, their gravitational effects on surrounding matter and space-time, their role in astrophysical processes like the production of jets and accretion disks, and increasingly their merger dynamics as revealed by gravitational wave detections. These aspects are firmly established and repeatedly confirmed by observations. Between these domains of the known and the unknown lies a gradient of theoretical understanding with varying degrees of certainty, from the relatively well-established physics just inside the event horizon to the increasingly speculative approaches to the singularity. This gradient reflects not just the specific challenges of black hole physics, but the nature of scientific knowledge more generally, its progression from established principles through reasonable extrapolations to speculative frontiers. The black hole serves as a kind of cosmic Rorschach test, revealing through our attempts to understand it not just the nature of these extreme objects, but the character and limitations of our scientific approach to reality. It shows us both the remarkable power of theoretical physics to explore domains beyond direct experience and the inherent limitations of any theoretical framework when pushed to its extremes. In this way, the black hole is indeed not just a cosmic trap, but a mirror of mystery itself, reflecting back to us the strengths and limitations of our quest for understanding. It reminds us that science is not a completed edifice, but an ongoing process, a journey toward greater comprehension that never reaches a final destination, but continues to reveal new questions, new challenges, and new frontiers of knowledge. As we continue our theoretical journey, we carry with us this awareness of both the power and the limitations of scientific knowledge. We recognize that some aspects of black holes may remain permanently beyond our full comprehension, while others may yield to future theoretical advances and observational techniques. We embrace both the known and the unknown, the certainties and the mysteries, as essential aspects of our cosmic exploration. What you are may not end with what you know yourself to be. As our theoretical journey through a black hole approaches its conclusion, we turn to perhaps the most profound questions of all. What might happen to consciousness in such an extreme environment? Could any form of awareness or subjective experience survive the journey to and beyond the event horizon? And what do black holes tell us about the ultimate fate of consciousness in the cosmos? These questions take us beyond conventional physics into domains where science meets philosophy, where objective descriptions of physical processes intersect with the subjective reality of experience. While we cannot provide definitive answers, we can explore possibilities that emerge from our current understanding and from more speculative extensions of that understanding. For a biological consciousness like our own, the prospects for survival in a black hole seem grim. As we have seen, the tidal forces near the singularity would ultimately tear apart any physical structure, regardless of its composition or strength. The human brain, the physical substrate that generates our consciousness, would be destroyed long before reaching the central regions of the black hole. From this perspective, consciousness would simply cease when its physical basis is disrupted beyond the point where it can maintain the integrated information processing that constitutes awareness. Yet this straightforward conclusion rests on certain assumptions about the nature of consciousness, assumptions that some philosophers and scientists have questioned. The conventional scientific view sees consciousness as emergent from or identical to certain physical processes in the brain. But alternative perspectives suggest consciousness might have aspects that transcend its particular physical implementation. Some approaches to the mind-body problem, such as certain forms of panpsychism, suggest that consciousness might be a fundamental feature of reality, rather than merely an emergent property of complex systems. Others, drawing on interpretations of quantum mechanics, propose connections between consciousness and quantum processes that might behave differently than classical physics would predict in extreme environments. If any of these alternative perspectives has merit, the fate of consciousness in a black hole might be more complex than simple destruction. Perhaps some aspect of consciousness could persist even as its physical substrate is transformed, not as a continuation of individual identity, but as a more fundamental form of awareness or information processing that transcends particular physical structures. This speculation connects to questions about the nature of information in black holes that we explored earlier. If information is not truly destroyed, but transformed and eventually returned to the universe through Hawking radiation, might something similar apply to the information patterns that constitute consciousness? Might these patterns be preserved in some form, encoded perhaps in subtle quantum correlations or in the holographic description on the event horizon? For biological consciousness, such preservation would not mean survival in any conventional sense. The specific patterns of neural activity that constitute our individual awareness would be thoroughly disrupted and transformed beyond recognition. But if consciousness has aspects that are more fundamental than particular neural patterns, something might persist through this transformation, though it would bear little resemblance to human experience as we know it. Moving beyond biological consciousness, we might consider more speculative possibilities for future forms of awareness. If consciousness can be instantiated in substrates other than biological brains, such as advanced computational systems or other technologies yet to be developed, might these alternative forms have different prospects for survival in extreme environments? Advanced artificial intelligence systems, for instance, might be designed with distributed processing capabilities and error correction mechanisms that make them more resilient to physical disruption than biological brains. Such systems might maintain functional coherence longer in the face of increasing tidal forces. Yet even these would ultimately succumb to the extreme conditions near the singularity. More radical possibilities emerge if we consider consciousness that has been entirely uploaded or transferred to informational or energy-based substrates. Such transformed consciousness might interact with the physics of a black hole in ways very different from material objects. While still subject to the fundamental constraints of physics, information might be preserved or transformed rather than destroyed, particularly if the holographic principle applies and information is encoded on the horizon, even as physical structures pass through it. These speculations about advanced or transformed consciousness highlight another aspect of the relationship between black holes and the fate of awareness in the cosmos. Black holes may play an important role in the long-term future of consciousness, whether biological, artificial, or transformed into states we can barely imagine. As the universe continues to expand and cool over trillions of years, conventional energy sources like stars will eventually be exhausted. In these far future epochs, black holes may become crucial resources for any surviving advanced civilizations. The energy contained in rotating black holes, potentially extractable through processes like the Penrose process, might power continued information processing, and thus consciousness long after stars have gone dark. Even more intriguing is the relationship between black holes and the flow of time. Near a black hole's event horizon, time dilation becomes extreme. 1 hour near the horizon might correspond to thousands or millions of years for distant observers. For any form of consciousness that could survive near such a boundary, this time dilation effect might offer a way to witness cosmic evolution at an accelerated pace, or to effectively travel into the distant future relative to the rest of the universe. Some speculative scenarios for the far future of consciousness involve using these time dilation effects to survive across cosmological timescales, perhaps waiting in a state of slowed subjective time for conditions more favorable to continuation or transformation. Black holes, in this view, might serve not just as destructive cosmic traps, but as temporal refuges, regions where consciousness might persist as the universe around it ages at a dramatically accelerated rate. The Schwarzschild eternal black hole solution to Einstein's equations even suggests more exotic possibilities, with its mathematical description of a white hole connected to the black hole, potentially opening into another universe or another region of our universe. While traversing such a connection would likely be physically impossible for macroscopic objects, it raises the question of whether information or patterns that constitute consciousness might in some way pass through such a theoretical bridge. All of these speculations remain far removed from what current physics can confirm or even meaningfully analyze. They represent not scientific predictions, but explorations of possibility, attempts to connect what we know about these extreme cosmic objects with philosophical questions about the nature and fate of consciousness. What emerges from these explorations is a profound sense of both the vulnerability and the potential resilience of consciousness in the cosmos. Biological consciousness, tied to specific physical structures evolved for conditions on the surface of a small rocky planet, is indeed fragile when confronted with the extreme physics of black holes or other cosmic cataclysms. Yet consciousness in a broader sense, understood as information processing or as patterns that could potentially be instantiated in multiple substrates, might have more pathways for continuation or transformation than we can currently envision. The study of black holes reminds us that consciousness, like everything else in the universe, exists within the context of physical laws and constraints. Yet it also hints at the possibility that the relationship between consciousness and physical reality might be more complex and more profound than our current understanding suggests. As we contemplate the fate of consciousness in and around black holes, we're reminded of how much remains unknown about both these cosmic objects and about awareness itself. The physics of black holes pushes our theories to their limits and beyond. The nature of consciousness remains one of the greatest unsolved problems in science and philosophy. Their intersection represents a domain of profound mystery and possibility. For our theoretical journey, these reflections on consciousness and cosmic fate provide a fitting approach to our conclusion. We have ventured in imagination to the most extreme environment known to physics, a place where space and time themselves are warped beyond recognition, where known physical laws begin to break down and where new physics must enter. We have considered not just the fate of matter and energy in such an environment, but the possible fate of awareness itself. In doing so, we have confronted the limits of current knowledge and glimpsed the vast territories of the unknown that lie beyond. We have seen how black holes serve not just as subjects of scientific study, but as catalysts for deeper questions about the nature of reality, information, and consciousness. And we have considered how these cosmic objects might relate to the long-term future of awareness in the universe, whether in forms familiar to us or in states we can barely imagine. What you are may not end with what you know yourself to be. This theme, suggested in the chapter title, applies both to the potential transformation of consciousness in extreme environments and to our scientific and philosophical understanding more broadly. What we are as conscious beings and as a species seeking to comprehend the cosmos extends beyond our current self-conception. The study of black holes, by pushing us to the very frontiers of knowledge, helps us glimpse aspects of reality and possibility that transcend our ordinary understanding. And so our journey continues, not just through the theoretical interior of a black hole, but through the ongoing human quest to understand our place in the cosmos and the nature of consciousness itself. The black hole, with its profound mysteries and its challenge to our most fundamental theories, serves as both a physical reality to be studied and a powerful metaphor for the limits and possibilities of knowledge and awareness. In a place without time, what does it mean to be lost? As we approach the final chapter of our theoretical journey into a black hole, we confront perhaps the most profound and disorienting aspect of these cosmic objects, the way they transform our experience of time itself. Inside the event horizon, as we've explored in earlier chapters, the roles of space and time begin to shift. What was once a spatial direction, the radial coordinate pointing toward or away from the center of the black hole, takes on aspects of time. Movement toward the singularity becomes as inevitable as the forward flow of time outside the black hole. This transformation creates a state that we might describe as falling forever, a condition where the ordinary relationship between time, space, distance, and duration breaks down. To explore this strange state, let us consider different perspectives on time within a black hole and what they might mean for our subjective experience. Were we somehow able to maintain awareness during this final phase of our journey? From the perspective of an outside observer, someone watching from a safe distance as an object falls toward a black hole, time appears to slow asymptotically as the object approaches the event horizon. Due to the extreme gravitational time dilation, the infalling object seems to move more and more slowly, never quite reaching the horizon itself. Its image reddens and dims as the light it emits is stretched to longer wavelengths and lower energies, eventually fading from visibility altogether. For the outside observer, the object's fall takes an infinite amount of time. In this sense, falling into a black hole is a journey that, from the external perspective, is never completed. The object becomes frozen at the horizon, suspended in a state of eternal approach, a ghost image slowly fading from the visible universe, but never quite vanishing completely in any finite time. Yet from the perspective of the falling object itself, the journey continues past the horizon in a finite and typically brief time. There is no physical barrier or boundary that it experiences when crossing the event horizon, no sudden change in local conditions. The crossing is notable only for what becomes impossible afterward, the inability to send signals back to the outside universe, not for any dramatic change in the immediate environment. Once inside the horizon, the falling object continues its journey toward the singularity. For a non-rotating Schwarzschild black hole, this journey necessarily ends at the central singularity in a finite amount of proper time, the time measured by an imaginary clock traveling with the object. No amount of thrust or acceleration can prevent this encounter, as all possible future light cones, all possible paths through space-time, lead inexorably inward. For a rotating Kerr black hole, the situation becomes more complex. The central singularity takes the form of a ring rather than a point, and in principle, an object could pass through the center of this ring without encountering the singularity itself. Some solutions to Einstein's equations suggest the possibility of continuing through to another region of space-time, perhaps another universe or another part of our universe. However, most physicists believe that in realistic black holes, instabilities would make this passage impossible, effectively closing off any such tunnel. These different perspectives on time, the infinite duration perceived by outside observers versus the finite journey experienced by the falling object, create a paradoxical situation. From the outside, nothing ever quite reaches the black hole. From the inside, objects not only reach but pass through the horizon and continue toward the center. These are not contradictory descriptions but complementary ones, different ways of describing the same physical reality from different reference frames. This duality of perspectives mirrors in some ways the wave-particle duality in quantum mechanics or the complementarity principle in the interpretation of black hole information. Different descriptions, seemingly at odds, turn out to be different aspects of a more complex and subtle reality that transcends our intuitive understanding. For our theoretical falling observer, the experience of time inside the black hole would be profoundly altered. As they approach the singularity, several effects would combine to create a state unlike anything experienced in normal space-time. First, the tidal forces would become increasingly severe, stretching and compressing any physical object along different axes. For a human or any biological entity, these forces would quickly become fatal, tearing apart tissues, cells, molecules, and eventually atoms themselves. But for a purely theoretical observer, one somehow able to maintain awareness despite these forces, the experience would be of accelerating distortion, a physical stretching that would continue to intensify without bound. Second, the curvature of space-time would become so extreme that normal concepts of distance and direction would lose their usual meaning. The singularity would not appear as a point in space toward which the observer was moving, but as a future moment in time that the observer was approaching, a moment when space-time curvature becomes infinite and current physical theories break down. Third, the light cones, which describe the possible paths of light and therefore all causal relationships, would become increasingly tilted and narrowed until all possible future paths led to the singularity. The observer would experience not just physical constraint, but a fundamental constriction of possibility itself, a narrowing of all future options to a single inevitable destination. In this environment, where space and time exchange aspects and where all paths lead to a singular future, what might it mean to fall forever? The paradox lies in the contrast between the finite proper time of the journey, as measured by the falling observer, and the sense of eternity or endlessness that might characterize the subjective experience. Even in normal circumstances, our subjective experience of time can differ dramatically from clock time. Moments of extreme danger or intense concentration can seem to stretch out as our awareness becomes more focused and our neural processing creates a slow motion effect. Conversely, periods of routine activity can seem to compress, with hours or even days passing almost unnoticed. This malleability of subjective time might be amplified to an extreme degree in the final approach to a black hole singularity. Some philosophers and physicists have speculated that as an observer approached the singularity, subjective time might extend dramatically, creating an experience where each remaining second of proper time contains what feels like an eternity of awareness. This would not violate any physical laws, as it concerns subjective experience rather than objective measurement, but it suggests a strange kind of immortality, a falling forever within a journey that objectively takes only a finite time to complete. Others have proposed that the breakdown of normal space-time near the singularity might create a state where the usual distinctions between past, present, and future begin to blur or dissolve. In such a state, linear temporal experience might give way to something more holistic or integrated, a perception not of moments in sequence, but of temporal reality as a unified whole. This would be not so much falling forever as falling outside of time as we understand it. These speculations about subjective experience near a singularity connect to broader philosophical questions about the nature of time itself. Is time a fundamental aspect of physical reality, as most of our current theories assume? Or is it, as some philosophers and physicists have suggested, an emergent property, a way our minds organize experience rather than an intrinsic feature of the universe. Black holes, particularly their interiors, provide a theoretical laboratory for exploring such questions. They represent environments where our conventional understanding of time breaks down, where the distinction between space and time becomes fluid, and where we are forced to confront the possibility that our familiar temporal experience is just one way of perceiving a reality that at its deepest levels might transcend such categories entirely. For our falling observer, suspended between the finite proper time of the journey and the potentially infinite subjective extension of experience, the state might be described as a kind of temporal twilight, neither fully within time as we normally understand it, nor completely beyond it. It is a state of transition or transformation, a passage from the familiar temporal reality of the outside universe to whatever might lie at or beyond the singularity. This state of falling forever also connects to the question of what it means to be lost. In ordinary experience, being lost implies a separation from the familiar, a dislocation in space, a severing of known references and connections. Inside a black hole, particularly in the final approach to the singularity, this lostness takes on a more profound dimension. The falling observer is lost not just in space, but in space-time itself, adrift in a region where the normal references that orient our existence, the very structure of forward-moving time and three-dimensional space, have been warped beyond recognition. It is a lostness more fundamental than any geographical disorientation, a cosmic lostness where the familiar landmarks of reality itself have been left behind. Yet, there is a paradoxical aspect to this lostness as well. While separated from the familiar universe outside, the falling observer is also on a path of absolute certainty, moving inevitably toward the singularity. In a sense, it is impossible to be truly lost inside a black hole, as all paths lead to the same destination. It is a state of maximum disorientation, combined with maximum determinism, of being utterly lost while having one's path completely determined. This paradoxical state, falling forever while on a journey of finite duration, lost in space-time while following the only possible path, reflects the broader paradoxes that black holes present to our understanding. They are regions where the seemingly contradictory becomes complementary, where different perspectives reveal different aspects of a reality that transcends our intuitive categories. As our theoretical journey approaches its conclusion, we find ourselves in this strange twilight state, falling toward a destination that represents both an ending and a question mark. The singularity ahead marks the point where our current physical theories break down, where mathematical infinities signal the need for new frameworks, new ways of understanding the nature of space, time, matter, and perhaps consciousness itself. In this final approach, we are suspended between knowing and unknowing, between the physics we understand and the domains where that understanding fails, between the finite and the infinite. We are falling forever in a journey that must end, lost in a place where all paths are determined, approaching a point that represents both the ultimate constraint and the ultimate mystery. This state of paradox and liminality, of being between categories and beyond familiar reference points, might be the most accurate description of what it means to fall forever inside a black hole. It is not a state that can be fully captured in the language of conventional physics or everyday experience. It requires a more poetic, more philosophical approach, one that embraces paradox and acknowledges the limits of our understanding. In a place without time as we know it, being lost takes on new meanings. It becomes not just a practical condition, but an ontological one, a transformation of being itself. What was once a conscious entity moving through space-time becomes something else entirely, neither fully present nor fully absent, neither entirely destroyed nor meaningfully preserved in any familiar form. As we contemplate this state of falling forever, of being lost in a place where time and space have exchanged roles, and where all futures lead to a single point, we approach the limits, not just of our physics, but of our language and thought. We enter domains where metaphor and mathematics must work together to gesture toward realities that transcend direct description. And perhaps this is fitting for the conclusion of our journey. Black holes, after all, are not just physical objects, but gateways to new understanding. catalysts for questions that challenge our most fundamental assumptions about the nature of reality, in a place without time as we know it. What does it mean to be lost? It means to be transformed beyond recognition, to exist in a state that transcends our familiar categories, to approach a boundary where current understanding ends and new possibilities begin. It is to fall forever in a finite journey, to be simultaneously constrained to a single path and adrift in a domain where the familiar landmarks of reality have disappeared. As our theoretical journey reaches its conclusion, we remain suspended in this paradoxical state, falling toward a destination that represents both an ending and a question, a point where current physics breaks down and where new physics, perhaps revealing new aspects of reality beyond our current comprehension, must take its place.